In 2005, telescopes picked up something strange, an explosion so powerful it outshone 1 million suns in just a few seconds. A gamma-ray burst, they called it. But where it came from? Still a mystery. That was just one sign. Out in the vast silence of space, there are places we still don't understand. Black holes that swallow light, galaxies that whisper secrets across billions of years, strange signals, shadows that don't make sense, and flashes of energy we can't explain. We've mapped our solar system, sent probes past the edge of the sun's reach, but when it comes to the deeper galaxy, we're still blind. The universe is old, quiet, but never still. Before we start today's journey, let us know where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a ride to the most dangerous object in space. Space, in its immense and seemingly tranquil expanse, harbours profound dangers. While often depicted as a serene backdrop for celestial bodies, the universe is a dynamic and sometimes violent arena where events unfold on scales incomprehensible to human experience. These threats are not merely theoretical. They are fundamental aspects of cosmic mechanics, capable of reshaping planetary systems, sterilizing worlds, and altering the very fabric of galaxies. Understanding these dangers requires acknowledging the raw power inherent in the cosmos, far beyond the familiar confines of our home planet. One of the most immediate and tangible threats in space comes from asteroids and comets. These rocky or icy remnants from the early solar system constantly traverse orbital paths, some of which intersect with Earth's trajectory. While most are small and burn up harmlessly in the atmosphere, larger objects possess the kinetic energy to cause catastrophic impacts. An impact event, depending on the size and composition of the object, could unleash energy equivalent to many thousands of nuclear bombs. Such an event could trigger widespread tsunamis, massive dust clouds blocking sunlight for extended periods, and global climate disruption, leading to mass extinctions. The geological record of Earth provides clear evidence of past impacts, demonstrating their capacity to profoundly alter life on a planetary scale. For instance, the event approximately 66 million years ago, widely believed to have caused the extinction of the dinosaurs, involved an asteroid impact that created a crater over 100 miles wide. Beyond our solar system, stars themselves, the very sources of light and life, can become agents of destruction. The most dramatic stellar events are supernovae, the explosive deaths of massive stars. When a star significantly more massive than our Sun exhausts its nuclear fuel, its core collapses under its own gravity, triggering an explosion that can briefly outshine an entire galaxy. A supernova explosion releases an enormous burst of energy, including intense radiation across the electromagnetic spectrum, from X-rays to gamma rays, and a powerful shockwave of high-energy particles. If a supernova were to occur within a few tens of light years of Earth, the resulting radiation could strip away our planet's ozone layer, exposing life to lethal levels of ultraviolet radiation. The high-energy particles could also cause widespread genetic damage and disrupt electronic systems. Even at greater distances, the lingering effects of a supernova, such as cosmic rays, could still pose a long-term threat to biological systems. Even more energetic than typical supernovae are gamma-ray bursts, or GRBs. These are the most powerful explosions known in the universe, releasing more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. GRBs are thought to originate from two primary sources: the collapse of very massive, rapidly rotating stars into black holes, or the merger of two neutron stars. These events produce tightly focused beams of gamma rays that travel across vast cosmic distances. If one of these beams were to sweep across a planetary system like ours, the consequences would be devastating. The intense burst of gamma rays would ionize the upper atmosphere, creating nitrogen oxides that would deplete the ozone layer. This would expose the planet's surface to a deluge of harmful ultraviolet radiation from its own star, potentially leading to mass extinctions and long-term environmental changes. The rarity and directional nature of GRBs make a direct hit on Earth unlikely, but their sheer power makes them a significant cosmic danger. Black holes represent another profound cosmic threat. These regions of space-time exhibit such strong gravitational effects that nothing, not even particles and electromagnetic radiation such as light, can escape from inside them. Stellar mass black holes form from the collapse of massive stars, while supermassive black holes reside at the centers of most galaxies, including our own Milky Way. While black holes do not suck things in from vast distances like cosmic vacuum cleaners, any object that ventures too close to their event horizon, the point of no return will be irrevocably drawn in. For a star or planet approaching a black hole too closely would result in spaghettification, where the object is stretched and torn apart by immense tidal forces before being consumed. Furthermore, the accretion disks that form around active black holes, where gas and dust spiral inward, can generate powerful jets of high-energy particles and radiation capable of sterilizing vast regions of space. Cosmic rays, high-energy particles that travel through space at nearly the speed of light, also pose a continuous, albeit less dramatic, threat. These particles originate from various energetic events, including supernovae, active galactic nuclei, and possibly other extreme cosmic phenomena. While Earth's magnetic field and atmosphere offer significant protection, some cosmic rays still reach the surface. For astronauts in space, particularly on long-duration missions beyond Earth's protective magnetic field, exposure to cosmic rays is a serious concern, potentially causing radiation sickness, cancer, and damage to electronic equipment. On a galactic scale, sustained bombardment by intense cosmic rays could influence planetary atmospheres and even the evolution of life. Galactic collisions, while occurring over immense timescales, represent another form of cosmic danger. Galaxies are not static entities. They move through space and can interact with one another. Our own Milky Way galaxy is on a collision course with the Andromeda Galaxy, an event predicted to occur in approximately 4.5 billion years. While direct star-on-star collisions are extremely rare due to the vast distances between stars within galaxies, the gravitational interactions during a galactic merger can significantly disrupt stellar orbits, eject stars and planetary systems into intergalactic space, and trigger bursts of star formation and supermassive black hole activity. The overall structure of both galaxies would be dramatically altered, creating a new, larger galaxy. Finally, the vacuum of space itself, with its extreme temperatures and lack of atmosphere, is inherently hostile to life as we know it. Unprotected exposure to the vacuum would lead to rapid decompression, boiling of bodily fluids, and freezing. The vast emptiness also means that resources are incredibly sparse, and travel between celestial bodies requires immense energy and time. These fundamental conditions underscore the inherent challenges and dangers of operating and surviving in the cosmic environment, making it a place of both profound beauty and formidable peril. A star is a massive luminous sphere of plasma held together by its own gravity. It is a celestial body that generates light and heat through nuclear fusion reactions occurring in its core. The most common type of fusion reaction in stars involves hydrogen atoms combining to form helium, a process that releases enormous amounts of energy. This outward pressure from fusion balances the inward pull of gravity, creating a stable state known as hydrostatic equilibrium, which allows stars to exist for millions or billions of years. The formation of a star begins within vast clouds of gas and dust known as nebulae. These nebulae are primarily composed of hydrogen and helium, along with trace amounts of heavier elements. Within these clouds, denser regions can begin to collapse under their own gravitational attraction. As a region collapses, the material within it becomes more concentrated, and the gravitational pull intensifies, drawing in more surrounding gas and dust. This collapsing mass starts to heat up due to the increasing pressure. As the collapse continues, the core of the collapsing cloud becomes hotter and denser, forming a protostar. The protostar continues to accumulate mass from the surrounding nebula, and its temperature and pressure rise steadily. At this stage, the protostar is not yet undergoing nuclear fusion. It glows primarily from the heat generated by its gravitational contraction. This phase can last for hundreds of thousands to millions of years, depending on the star's eventual mass. Eventually, if the protostar accumulates enough mass, the temperature and pressure in its core reach a critical point, approximately 15 million degrees Celsius. At this extreme temperature and pressure, hydrogen nuclei begin to fuse together to form helium nuclei. This process, known as nuclear fusion, releases a tremendous amount of energy in the form of light and heat. When nuclear fusion ignites in the core, the protostar officially becomes a main sequence star. Our Sun is currently a main sequence star. The life cycle of a star is primarily determined by its initial mass. Stars can range in mass from about 8% of the Sun's mass to more than 100 times the Sun's mass. The more massive a star is, the hotter its core must be to maintain equilibrium, and thus the faster it consumes its nuclear fuel. Consequently, more massive stars have shorter lifespans than less massive ones. For stars like our Sun, which are considered low to medium mass stars, the main sequence phase lasts for billions of years. During this time, they stably fuse hydrogen into helium in their cores. When the hydrogen fuel in the core begins to deplete, the fusion reactions slow down. Without the outward pressure from fusion, gravity starts to win, causing the core to contract and heat up. This increased core temperature ignites hydrogen fusion in a shell surrounding the core. The energy from this shell fusion causes the outer layers of the star to expand dramatically and cool, turning the star into a red giant. The Sun will become a red giant in about 5 billion years, expanding to engulf the orbits of Mercury and Venus, and possibly Earth. After the red giant phase, the core of a Sun-like star continues to contract and heat up, until it becomes hot enough to fuse helium into carbon and oxygen. This helium fusion phase is relatively brief. Once the helium fuel in the core is exhausted, the star can no longer generate enough outward pressure to counteract gravity. The outer layers of the star are gently expelled into space, forming a beautiful expanding shell of gas called a planetary nebula. The exposed core, now a very dense hot remnant composed primarily of carbon and oxygen, is called a white dwarf. A white dwarf no longer undergoes fusion. It slowly cools down over billions of years, eventually becoming a cold, dark black dwarf, though the universe is not old enough for any black dwarfs to have formed yet. For stars much more massive than our Sun, those with masses greater than about 8 times the Sun's mass, the life cycle is far more dramatic and ends in a spectacular explosion. These massive stars also spend their main sequence phase fusing hydrogen into helium. However, due to their higher mass, their cores are much hotter and denser, allowing them to fuse heavier elements after hydrogen and helium are exhausted. They proceed through successive stages of fusion, creating elements like carbon, oxygen, neon, magnesium, silicon, and finally iron in their cores. Iron is a crucial element in this process because its fusion does not release energy. Instead, it consumes energy. Once the core of a massive star becomes predominantly iron, fusion stops. Without the outward pressure from fusion, the iron core rapidly collapses under its own immense gravity in a fraction of a second. This catastrophic collapse creates a powerful shock wave that rebounds off the superdense core, blasting the star's outer layers into space in a tremendous explosion called a supernova. The supernova explosion briefly shines with the light of an entire galaxy. What remains after a supernova depends on the initial mass of the star's core. If the core's mass is between about 1.4 and 3 times the mass of the Sun, the intense pressure of the collapse forces protons and electrons to combine into neutrons, forming an incredibly dense object called a neutron star. A neutron star is typically only about 12 miles in diameter, but contains more mass than the entire Sun. If the core's mass is greater than about 3 times the mass of the Sun, the gravitational collapse is so extreme that nothing can stop it, and the core continues to collapse into an infinitely dense point, forming a black hole, a region of space-time from which nothing, not even light, can escape. Stars are fundamental building blocks of galaxies, producing the heavy elements necessary for the formation of planets and life through their fusion processes and supernova explosions. They are the cosmic furnaces that recycle matter and energy throughout the universe. While the fundamental process of nuclear fusion defines all stars, not all stars are alike, and some possess properties that make them far more extreme and potentially dangerous than others. Our Sun, for example, is a relatively stable, medium-sized star, quietly fusing hydrogen into helium for billions of years. However, the universe is home to a diverse array of stellar objects, many of which exhibit behaviors and characteristics. That deviate significantly from the norm, ranging from the incredibly massive to the extraordinarily dense and magnetically charged. One major category of stars that differ from our Sun are the massive stars. These are stars born with initial masses greater than about 8 times the mass of the Sun. Unlike our Sun, which will live for approximately 10 billion years, massive stars have significantly shorter and more dramatic lives, often lasting only a few million years. Their immense gravity leads to much higher core temperatures and pressures, causing them to burn through their nuclear fuel at an astonishing rate. This rapid consumption of fuel means they quickly exhaust their hydrogen, then helium, and proceed to fuse heavier elements like carbon, oxygen, and eventually iron in their cores. The end of their lives is not a gentle fading into a white dwarf, but a spectacular and violent supernova explosion, which can be a significant cosmic danger as discussed previously. These stars are often found in young, active star-forming regions within galaxies. Among the remnants of these massive stars are neutron stars, which are perhaps the most extreme objects born from stellar death, besides black holes. A neutron star forms when a massive star undergoes a supernova explosion, and its core collapses to an incredibly dense state. A typical neutron star has a mass greater than our Sun, but is compressed into a sphere only about 12 miles in diameter, roughly the size of a city. This makes them extraordinarily dense. A single teaspoon of neutron star material would weigh billions of tons on Earth. Their extreme density results in immense gravitational fields, second only to black holes. Many neutron stars are also rapidly rotating, and if their magnetic poles are aligned with Earth's line of sight, they can appear as pulsars, emitting regular pulses of radio waves. A particularly unusual and dangerous type of neutron star is a magnetar. Magnetars are characterized by magnetic fields that are thousands of times stronger than those of typical neutron stars and quadrillions of times stronger than Earth's magnetic field. These incredibly powerful magnetic fields can cause starquakes on the magnetar's surface, which release enormous bursts of X-rays and gamma rays, known as soft gamma repeaters, or anomalous X-ray pulsars. These bursts are so powerful that if a magnetar were located relatively close to Earth, even at a distance of tens of thousands of light years, its burst could potentially disrupt Earth's magnetosphere and ionosphere, affecting satellites and communication systems. The sheer energy released in a magnetar flare is a testament to the extreme physics at play within these exotic stellar remnants. Another class of stars that are not normal in their behavior are those found in close binary systems. While many stars exist in binary or multiple star systems, close binaries can lead to unusual and sometimes violent phenomena. In some close binary systems, one star, typically a white dwarf, neutron star, or black hole, can gravitationally pull matter from its companion star. This process, called accretion, can lead to dramatic events. For instance, if a white dwarf accretes enough hydrogen from its companion, the accumulated hydrogen on its surface can ignite in a runaway nuclear fusion reaction, causing a powerful but non-destructive explosion known as a nova. This is a temporary brightening of the star, thousands of times its normal luminosity. More dangerously, if a white dwarf in a binary system accretes enough mass to exceed a critical limit, known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, it can undergo a type Ia supernova. Unlike the core collapse supernova of massive stars, a type Ia supernova involves the complete thermonuclear detonation of the white dwarf itself. These explosions are incredibly bright and are used by astronomers as standard candles to measure cosmic distances. While less energetic than core collapse supernovae, a type Ia supernova occurring too close to Earth would still pose a significant threat due to the intense radiation and particle flux. Beyond these specific types, there are also rogue stars. These are stars that have been ejected from their home galaxies due to gravitational interactions, often during galactic mergers or close encounters with supermassive black holes. These stars travel through intergalactic space, unattached to any galaxy. While not inherently dangerous in their stellar properties, Their unpredictable trajectories mean they could potentially pass through other galaxies or even planetary systems, causing gravitational perturbations that could disrupt orbits or trigger comet showers from outer solar system regions. Their isolation makes them difficult to track and predict. Even within the main sequence, there are stars significantly larger and more luminous than our Sun, such as blue giants, blue supergiants, and hypergiants. These stars are incredibly hot and bright, burning through their fuel at an immense rate. While they are stable during their main sequence phase, their extreme luminosity and powerful stellar winds can affect nearby planets, and their eventual supernova explosions are a certainty. Some hypergiants are also known for their instability, undergoing episodic mass loss or dramatic changes in brightness. The cosmos, in its vast and intricate tapestry, contains objects of profound extremes, and among the most remarkable and potentially dangerous are neutron stars, particularly a specialized subset known as magnetars. These are not ordinary stars. They are the super-dense, rapidly spinning remnants of once massive stars that met a spectacular end. To understand their danger, one must first grasp their fundamental nature, which defies everyday comprehension of matter and gravity. A neutron star is born from the catastrophic gravitational collapse of the core of a massive star after it has exhausted its nuclear fuel and undergone a supernova explosion. What is left behind is not a gas giant or a rocky planet, but an object of unimaginable density, where the very atoms have been crushed out of existence. Imagine taking something with more mass than our entire Sun and compressing it into a sphere only about 12 miles in diameter, roughly the size of a small city. This is the scale of a typical neutron star. Its mass can range from about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, up to possibly 2.3 times the mass of the Sun, though the exact upper limit is still a subject of active research. Within this incredibly compact volume, matter exists in a state unlike anything found on Earth. The immense gravitational forces are so powerful that they overcome the electron degeneracy pressure that supports white dwarfs, forcing protons and electrons to merge into neutrons. The star is, in essence, a giant atomic nucleus. This extreme compression gives neutron stars their defining characteristic: extraordinary density. A single teaspoon of neutron star material would weigh billions of tons on Earth, equivalent to the mass of all the cars in the United States combined. Beyond their incredible density, neutron stars possess other extreme properties. Many of them spin at astonishing rates, often completing hundreds of rotations per second. This rapid rotation is a consequence of the conservation of angular momentum during the core collapse. As the massive star's core shrinks dramatically, its rotation speeds up, much like a figure skater pulling in their arms. If a neutron star's magnetic poles are aligned in such a way that their beams of radiation sweep across Earth, we observe them as pulsars, emitting precise, regular pulses of radio waves, much like a cosmic lighthouse. These pulses are incredibly stable, making pulsars some of the most accurate clocks in the universe. However, the danger of a neutron star is amplified when it belongs to the rare class of magnetars. Magnetars are neutron stars endowed with magnetic fields that are orders of magnitude stronger than any other known object in the universe. While typical neutron stars have magnetic fields trillions of times stronger than Earth's, a magnetar's magnetic field can be 1,000 times stronger still, reaching quadrillions of times the strength of Earth's field. To put this in perspective, if a magnetar were located halfway to the Moon, its magnetic field would be strong enough to erase the data on every credit card on Earth. The origin of these extreme magnetic fields is thought to be tied to the rapid rotation and convection within the star's core during its formation, amplifying a relatively modest initial magnetic field to these incredible strengths. The energy stored within a magnetar's magnetic field is immense, comparable to the energy released by a supernova explosion over a short period. It is this unparalleled magnetic field that makes magnetars particularly dangerous. The magnetic field of a magnetar is so powerful that it can cause starquakes on the star's surface. These are sudden rearrangements and fractures of the star's solid crust, similar to earthquakes on Earth, but on a vastly more energetic scale. When these starquakes occur, they can trigger explosive releases of energy in the form of powerful bursts of X-rays and gamma rays. These events are known as soft gamma repeaters, or SGRs, and anomalous X-ray pulsars, or AXPs, which are two categories of magnetars identified by their characteristic emissions. A magnetar flare can release more energy in a fraction of a second than the Sun will produce in 100,000 years. The most powerful observed magnetar flare, from SGR 1806-20, occurred on December 27, 2004. This burst was so intense that it briefly affected Earth's ionosphere, even though the magnetar was located approximately 50,000 light-years away in another part of our galaxy. The burst was detected by satellites and even caused a measurable expansion of Earth's ionosphere, demonstrating the far-reaching effects of these cosmic cataclysms. The danger posed by a magnetar stems from the immense energy of these bursts and their potential to affect distant planetary systems. If a magnetar were to unleash a powerful gamma-ray burst, and that burst were directed towards Earth, the consequences could be catastrophic. While the likelihood of such an event happening within a dangerous proximity to Earth is extremely low, the sheer power of the burst warrants scientific concern. A direct hit from a gamma-ray burst could strip away Earth's protective ozone layer, leaving the surface exposed to lethal levels of ultraviolet radiation from the Sun. This could trigger mass extinctions and severely impact the planet's climate and ecosystems. The high-energy particles associated with such a burst could also damage electronic systems, disrupt power grids, and pose a severe radiation hazard to any life forms exposed. Furthermore, the extreme gravity of a neutron star, whether a magnetar or a more typical one, also presents a danger. While they do not suck things in from vast distances like black holes, any object that ventures too close would experience immense tidal forces. These forces would stretch and tear apart any star, planet, or spacecraft that approached within a certain critical distance, known as the tidal disruption radius, before it is consumed by the star's gravity. The escape velocity from a neutron star is incredibly high, approaching the speed of light, meaning that anything falling towards it would accelerate to extreme speeds. The intense gravitational field also causes a phenomenon known as gravitational lensing, where the star's gravity bends the path of light, distorting the images of objects behind it. The rogue aspect of some of these stars adds another layer to their potential danger. While many neutron stars remain within the galactic disk where they were born, some are ejected from their birthplaces at high velocities. This can happen due to an asymmetric supernova explosion, where the blast is stronger in one direction, giving the remnant a powerful kick, or through gravitational interactions with other massive objects in a dense stellar cluster. These rogue neutron stars can travel through intergalactic space or across the galactic disk. Their trajectory is largely unpredictable over long timescales. A rogue magnetar travelling at high speed could potentially pass through a star-forming region, a planetary system, or even another galaxy, causing gravitational disturbances or unleashing its powerful bursts in unexpected locations. While the vastness of space makes direct collisions or close encounters rare, the existence of such high-velocity, highly energetic objects underscores the dynamic and sometimes chaotic nature of the universe. In summary, a magnetar is a neutron star with an exceptionally powerful magnetic field. Its fundamental nature is defined by extreme density, rapid rotation, and a magnetic field that can store and release immense amounts of energy. This combination makes it a source of the most powerful explosions in the universe, the gamma-ray bursts and other high-energy flares. While these events are rare and typically occur far from Earth, their sheer destructive potential, coupled with the possibility of a rogue trajectory, places magnetars among the most fascinating and potentially dangerous objects in the cosmos. The birth of a neutron star, and by extension a magnetar, is not a gentle process but a cataclysmic event of unimaginable power, a supernova explosion. This fiery genesis represents the dramatic final act in the life cycle of a massive star, a cosmic spectacle that outshines entire galaxies for a brief period and reshapes its stellar neighbourhood. Understanding the extreme conditions and processes involved in a supernova is crucial to comprehending the fundamental nature of the dangerous star it leaves behind. A star destined to become a neutron star begins its life as a massive star, typically possessing at least 8 times the mass of our Sun. These stellar giants burn through their nuclear fuel at a prodigious rate, far faster than smaller stars like our Sun. For most of its life, such a star resides on the main sequence, fusing hydrogen into helium in its core, a process that generates the outward pressure balancing the inward pull of gravity. This allows it to continue fusion processes long after hydrogen is exhausted. Once the hydrogen in the core is depleted, the core contracts and heats up further, initiating the fusion of helium into carbon and oxygen. As the helium is consumed, the core contracts again, leading to the fusion of even heavier elements. This process continues in successive shells, like an onion, with lighter elements fusing in the outer shells and heavier elements fusing closer to the core. The star sequentially fuses carbon into neon, neon into oxygen and magnesium, and then silicon into iron. Each stage of fusion requires higher temperatures and pressures than the last, and each stage is progressively shorter, lasting from millions of years for hydrogen fusion down to mere days or even hours for silicon fusion. The formation of an iron core marks the beginning of the end for the massive star. Iron is a unique element in nuclear fusion because, unlike all lighter elements, its fusion does not release energy. Instead, it consumes energy. This is because iron nuclei are the most stable nuclei, meaning that fusing them or splitting them requires an input of energy rather than releasing it. Once the core is primarily composed of iron, it can no longer generate the outward pressure needed to counteract the immense gravitational force pressing inward. The delicate balance between gravity and fusion pressure is irrevocably broken. At this critical point, with no energy source to support it, the iron core begins to collapse with terrifying speed. In a fraction of a second, typically within a few hundred milliseconds, a core roughly the size of Earth collapses to a super-dense ball only about 12 miles across. This collapse occurs at speeds approaching 1/4 of the speed of light. As the core material is compressed to densities greater than that of an atomic nucleus, the protons and electrons are forced together to form neutrons, releasing a flood of neutrinos, tiny, weakly interacting particles. This sudden burst of neutrinos carries away a significant portion of the gravitational energy released by the collapse. The collapse of the core does not continue indefinitely. When the core reaches nuclear densities, it becomes incredibly stiff and incompressible, effectively bouncing back. The infalling material from the outer layers of the star slams into this newly formed super-dense neutron core. This collision generates a powerful outward-moving shockwave. Initially, this shockwave struggles to propagate through the dense overlying material of the star. For many years, the exact mechanism by which this shockwave is reinvigorated to explode the star was a puzzle. Current models suggest that the intense flux of neutrinos streaming out from the collapsing core plays a crucial role, depositing energy into the shockwave and helping it to blast through the star's outer layers. Once the shockwave successfully propagates, it violently expels the star's outer envelopes into space at speeds of thousands of miles per second. This is the supernova explosion. The amount of energy released in this event is staggering. For a brief period, typically a few weeks, the supernova can shine brighter than an entire galaxy of billions of stars. The light from a supernova is so intense that it can be seen across vast intergalactic distances. For instance, supernova 1987A, observed in the Large Magellanic Cloud, was visible to the naked eye from Earth, despite being over 160,000 light-years away. The supernova explosion is not just a burst of light, it is also a cosmic factory for heavy elements. While lighter elements up to iron are formed through fusion in the star's core during its life, elements heavier than iron, such as gold, silver, uranium and platinum, are primarily created during the extreme conditions of a supernova. The intense neutron flux during the core collapse and the subsequent explosion allows for rapid neutron capture processes, building up these heavier nuclei. These newly synthesized elements are then scattered throughout the galaxy by the expanding supernova remnant, enriching the interstellar medium. This enrichment is vital for the formation of new stars, planets, and ultimately life itself. Every atom of iron in our blood and every atom of gold in our jewelry was forged in the heart of a dying star and dispersed by a supernova. The conditions within a supernova are among the most extreme in the universe. Temperatures can reach billions of degrees Celsius, and pressures are immense, the explosion accelerates particles to nearly the speed of light, contributing to the cosmic ray background that permeates our galaxy. The initial burst of neutrinos and the subsequent flood of X-rays and gamma rays create a highly energetic and dangerous environment. The remnants of these explosions, the expanding shells of gas and dust known as supernova remnants, can persist for thousands of years, continuing to glow as they interact with the interstellar medium. These remnants are also sites where new stars can form, as the shock waves from the explosion can compress existing gas clouds, triggering gravitational collapse. What remains after the supernova explosion depends critically on the mass of the collapsing core. If the core's mass is between about 1.4 and 3 times the mass of the Sun, the neutron degeneracy pressure, a quantum mechanical effect, is sufficient to halt the collapse, resulting in the formation of a neutron star. If the core's mass exceeds this limit, typically around 3 solar masses, even the immense neutron degeneracy pressure is insufficient to prevent further collapse, and the core continues to shrink, forming a black hole, a region of space-time from which nothing can escape. The specific properties of the progenitor star, such as its initial mass, rotation rate, and metallicity, the abundance of elements heavier than hydrogen and helium, play a crucial role in determining the final outcome and whether the remnant will be a typical neutron star or the more exotic and dangerous magnetar. The rapid rotation of the progenitor star's core and strong magnetic fields are thought to be key ingredients in the birth of a magnetar. The concept of density, in its simplest form, refers to how much stuff is packed into a given space. We encounter density in our daily lives. A feather is less dense than a rock, and a rock is less dense than a piece of lead. However, the density found within a neutron star, the dangerous object at the heart of our discussion, pushes the boundaries of what is conceivable, representing one of the most extreme states of matter in the universe. Understanding this incredible compactness is key to grasping the star's immense gravitational power and its potential for cosmic impact. To appreciate the extreme density of a neutron star, let us begin with familiar comparisons. Water, a common substance, has a density of approximately 1 gram per cubic centimetre. A typical rock might be 2 or 3 times denser. Even lead, a very heavy metal, is only about 11 times denser than water. Our Sun, a massive star, has an average density of about 1.4 grams per cubic centimetre, which is surprisingly close to that of water, because it is mostly a vast ball of gas. A white dwarf, the remnant of a Sun-like star, is far denser. A teaspoon of white dwarf material would weigh several tons. This is already an astonishing level of compression, where electrons are packed tightly together, creating what is known as electron degeneracy pressure. However, a neutron star dwarfs even the white dwarf in terms of density. A neutron star has a mass greater than our entire Sun, yet it is compressed into a sphere with a diameter of only about 12 miles. This means that a single cubic centimetre of neutron star material, a volume roughly the size of a sugar cube, would weigh an astonishing 600 million tons. To put this into a more relatable context, imagine taking all the cars in the United States, which number over 250 million, and somehow compressing them into a single sugar cube. This is the level of density we're talking about inside a neutron star. A teaspoon of neutron star material would weigh billions of tons, equivalent to the mass of Mount Everest, or perhaps all the combined weight of all the humans on Earth. This is not merely dense, it is super dense, a state of matter beyond our everyday experience. This extreme density is a direct consequence of the neutron star's violent birth in a supernova explosion. When the core of a massive star collapses under its own immense gravity, the pressure becomes so overwhelming that it forces protons and electrons to combine, forming neutrons. This process eliminates the empty space that exists within atoms, where electrons orbit a nucleus. Instead, the entire star becomes a giant continuous atomic nucleus, composed almost entirely of neutrons packed tightly together. The force that resists further collapse is called neutron degeneracy pressure, a quantum mechanical phenomenon where neutrons resist being in the same quantum state, thus preventing them from occupying the same space. This pressure is incredibly powerful, but it has a limit. The matter inside a neutron star is not like solid rock or liquid water. It is a fluid of neutrons, often described as a neutron superfluid in the interior, where particles can flow without resistance. The outer crust of a neutron star is thought to be a solid lattice of neutron-rich atomic nuclei, surrounded by a sea of electrons. Below this crust, the pressure increases, and the matter transitions into a liquid-like state of neutrons, with a small admixture of protons and electrons. Deeper still, in the very core of the most massive neutron stars, the densities become so extreme that scientists speculate about even more exotic states of matter, such as a quark-gluon plasma, where the neutrons themselves might break down into their fundamental constituents, quarks. However, these extreme core conditions are still a subject of ongoing theoretical research and observational verification. The implications of such extreme density are profound. Firstly, the surface gravity of a neutron star is immense, billions of times stronger than Earth's gravity. If you were to stand on the surface of a neutron star, you would be instantly flattened by the overwhelming gravitational force. This extreme gravity also means that the escape velocity, the speed needed to escape the star's gravitational pull, is incredibly high, approaching half the speed of light. Nothing, not even light, can escape if it falls beyond a certain point, though neutron stars still have a physical surface, unlike black holes which are infinitely dense singularities. Secondly, the extreme density leads to powerful tidal forces. If any object, such as a planet or a smaller star, were to approach too close to a neutron star, the difference in gravitational pull across its length would be so immense that the object would be stretched and torn apart into a stream of particles, a process colloquially known as spaghettification, before being consumed by the neutron star's gravity. This is a testament to the sheer power of its gravitational field. Thirdly, the immense gravitational field of a neutron star significantly warps the fabric of spacetime around it. This phenomenon, predicted by Einstein's theory of general relativity, means that light rays passing near a neutron star are bent, causing a strong gravitational lensing effect. This can make it possible to see parts of the star's far side, effectively allowing us to see more than half of its surface at once. Time also slows down significantly in such a strong gravitational field, a phenomenon known as gravitational time dilation. Our understanding of this extreme density comes from a combination of theoretical physics and astronomical observations. Theoretical models of stellar collapse and the behavior of matter at nuclear densities predict the existence and properties of neutron stars. Observations of neutron stars in binary systems, where their mass can be precisely measured by observing their gravitational influence on a companion star, confirm these theoretical predictions. Furthermore, the detection of gravitational waves from the merger of two neutron stars has provided unprecedented insights into the properties of matter at these extreme densities, allowing scientists to constrain the size and stiffness of neutron stars. These mergers also provide direct evidence of the formation of heavy elements and the intense gravitational fields involved. The internal structure of a neutron star, while largely theoretical, is thought to consist of several layers, each with different properties due to the varying pressures and densities. Beneath the thin, solid crust, there is a liquid outer core composed mainly of neutrons, which are believed to be in a superfluid state, meaning they flow without any viscosity. Deeper still, in the inner core, the densities are so immense that the state of matter is uncertain, possibly involving exotic particles or a deconfined quark matter. The stability of a neutron star against further collapse is maintained by neutron degeneracy pressure, but this pressure has a limit. If a neutron star accretes too much mass, exceeding the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses, even neutron degeneracy pressure cannot support it, and it will collapse further to form a black hole. The extreme density of a neutron star is also intrinsically linked to its other defining characteristics, such as its rapid rotation and powerful magnetic field. The conservation of angular momentum during the collapse from a large, slowly rotating star to a tiny, rapidly spinning neutron star is a direct consequence of its extreme compression. Similarly, the magnetic field of the progenitor star is frozen in during the collapse and compressed into a much smaller volume, leading to an immense amplification of its strength, especially in the case of magnetars. This demonstrates how the fundamental property of extreme density underpins many of the dangerous and fascinating characteristics of these compact stellar remnants. The sheer unthinkability of packing so much mass into such a small volume challenges our everyday intuition and highlights the extraordinary physics at play in the most extreme corners of the universe. Among the incredibly dense and fast-spinning remnants of dead stars, known as neutron stars, exists an even more extraordinary and potentially dangerous type, the magneta. These cosmic objects are defined by their unbelievably powerful magnetic fields, forces so immense they reshape our understanding of physics and can have far-reaching effects across the galaxy. While all neutron stars possess strong magnetic fields, a magneta's field is on an entirely different scale, making it a true magnetic monster in the cosmos. To grasp the power of a magneta's magnetic field, it helps to start with a comparison. Earth has a magnetic field that protects us from harmful solar radiation. Its strength at the surface is measured in tiny units called Gauss, roughly half a Gauss. A refrigerator magnet is about 100 Gauss. A typical neutron star, born from the collapse of a massive star, inherits and amplifies its progenitor star's magnetic field to a strength of trillions of Gauss. This is already a phenomenal increase, a million times stronger than Earth's field. However, a magneta's magnetic field is 1,000 times stronger than even that of a normal neutron star, reaching values of quadrillions of Gauss, or one followed by 15 zeros. To put this into a more relatable perspective, if a magnetar were located just over 600 miles from Earth, its magnetic field would be strong enough to wipe every credit card on the planet and scramble all electronic devices. If it were located halfway to the Moon, it would likely strip the iron from your blood. These comparisons highlight the truly unprecedented scale of a magneta's magnetic force. The origin of these hyper-powerful magnetic fields is a subject of ongoing scientific research, but the leading theory involves a combination of factors during the magnetar's birth. As a massive star's core collapses during a supernova explosion, it spins up dramatically due to the conservation of angular momentum. Simultaneously, any magnetic field present in the original star is compressed into an incredibly small volume. This compression alone vastly increases the magnetic field strength. However, for a magnetar, this is not enough. Scientists believe that during the very brief period when the core is collapsing into a protoneutron star, intense convection currents, or churning motions, within the rapidly spinning superhot fluid combine with the rapid rotation to generate an incredibly efficient dynamo effect. This dynamo, similar in principle to how Earth's magnetic field is generated but on a far more energetic scale, amplifies the magnetic field to the extreme levels observed in magnetars. The precise conditions of the progenitor star's initial rotation and magnetic field are thought to play a crucial role in determining whether a neutron star evolves into a magnetar. The effects of such an extreme magnetic field are bizarre and profound, altering the very properties of space and matter. In the presence of a magnetar's field, atoms themselves would be severely distorted. Their electron orbitals, normally spherical or elliptical, would be stretched into long, thin cigar shapes, aligned with the magnetic field lines. Empty space, or the vacuum, in the vicinity of a magnetar can behave like a crystal, a phenomenon known as vacuum birefringence, where light passing through it would travel at different speeds depending on its polarization relative to the magnetic field. This is an effect predicted by quantum electrodynamics, the theory that combines quantum mechanics with special relativity, and it is only observable in magnetic fields of such extreme strength. The immense stresses and energy stored within a magnetar's magnetic field are not static. The field itself can twist, tangle, and evolve, placing enormous strain on the neutron star's solid crust. These stresses can build up over time until the crust cracks and rearranges, similar to an earthquake on Earth, but on a cosmic scale. These events are known as starquakes. When a starquake occurs, it can cause a sudden, violent release of the magnetic energy, unleashing powerful bursts of X-rays and gamma rays into space. These eruptions are the defining characteristic by which magnetars are typically identified and are known as soft gamma repeaters, or SGRs, and anomalous X-ray pulsars, or XPs. These terms refer to two categories of magnetars that exhibit these particular types of energetic outbursts. Magnetar flares are incredibly energetic phenomena. A typical small flare might release as much energy in a second as the Sun does in a year. However, magnetars are also capable of generating giant flares, which are orders of magnitude more powerful. These superflares are the largest explosions observed in the universe since the Big Bang, excluding gamma-ray bursts associated with the collapse of massive stars themselves. The most famous example of a magnetar giant flare occurred on December 27, 2004, from the magnetar SGR 1806-20, located approximately 50,000 light-years away in our own Milky Way galaxy. This burst was so extraordinarily powerful that it saturated gamma-ray detectors on Earth-orbiting satellites, even from such a vast distance. The burst released more energy in about 1/10 of a second than the Sun produces in 100,000 years. Its effects were even felt on Earth. It ionized our planet's upper atmosphere, causing a measurable expansion of the ionosphere and briefly disrupting radio communications. This event provided undeniable proof of the immense destructive potential of these magnetic monsters, even from across a significant portion of our galaxy. Observational evidence for magnetars primarily comes from their distinctive X-ray and gamma-ray emissions. Unlike regular pulsars, whose radio pulses are powered by their rotation, magnetars are primarily X-ray emitters, and their X-ray luminosity is far greater than what their rotational energy could sustain. This excess energy is thought to be powered by the decay and dissipation of their extreme magnetic fields. Astronomers also observe sudden changes in a magnetar's spin rate, or glitches, which are believed to be caused by the starquakes and crustal rearrangements that trigger the flares. The long-term monitoring of their X-ray emission and their characteristic bursting behavior allows scientists to identify and study these rare and enigmatic objects. Only a few dozen magnetars have been positively identified in our galaxy, making them a very small but extremely important subset of neutron stars. The unique physics of magnetars extends to their magnetosphere, the region around the star dominated by its magnetic field. This magnetosphere is filled with superhot plasma, composed of charged particles that are trapped and accelerated by the intense magnetic field lines. These particles are continually interacting with the magnetic field, generating the persistent X-ray emission characteristic of magnetars. When the magnetic field lines reconnect or snap under immense stress, it can accelerate these particles to incredibly high energies, leading to the powerful bursts of radiation. The gradual decay of the magnetic field over time, typically over tens of thousands of years, is believed to be the ultimate source of energy for the magnetar's activity, eventually leading it to become a dead magnetar, no longer capable of producing powerful flares, though it would still exist as a highly magnetized neutron star. Gamma-ray bursts, or GRBs, represent the most powerful explosions in the universe since the Big Bang. These fleeting yet incredibly energetic events are sudden, intense flashes of gamma rays, the highest energy form of light, lasting from milliseconds to several minutes. Their discovery was accidental and initially shrouded in secrecy during the Cold War. In the 1960s, American Vela satellites, designed to detect secret nuclear weapons tests on Earth, unexpectedly began detecting powerful bursts of gamma radiation originating from outer space. For years, the source of these mysterious bursts remained unknown, baffling astronomers. It was not until the 1990s, with the launch of more advanced gamma-ray observatories, that scientists began to unravel the true nature and cosmic origins of GRBs. There are two primary categories of gamma-ray bursts, distinguished by their duration: long GRBs and short GRBs. While both are immensely powerful, they are thought to arise from different astrophysical phenomena. Long GRBs, which last for more than 2 seconds, are now widely understood to be associated with the collapse of very massive, rapidly rotating stars, a specific type of supernova known as a hypernova, that give birth to a new black hole. Short GRBs, lasting less than 2 seconds, are believed to result from the merger of two compact stellar objects, typically two neutron stars or a neutron star and a black hole. Given the context of a single star as the dangerous object, our focus here will primarily be on the long GRBs, the extreme end products of massive stellar evolution, and the giant flares produced by magnetars, which are also sources of gamma rays. The mechanism behind long gamma ray bursts involves what is known as the collapsor model. This scenario begins with a massive star, perhaps 25 times the mass of the Sun or more, that is rapidly spinning and has shed its outer hydrogen layers. As this star exhausts its nuclear fuel, its core collapses under its own gravity. Unlike a typical supernova where the core collapses to form a neutron star and expels the outer layers, in a hypernova, the core is so massive that it continues to collapse beyond the neutron star stage, directly forming a black hole. As the black hole forms, the material from the collapsing stellar core rapidly spirals inward, forming a superheated accretion disk around the newborn black hole. Friction and magnetic forces within this disk generate immense temperatures and pressures. It is from this accretion disk that the highly collimated relativistic jets of matter are launched. These jets, powered by the black hole's immense gravity and the disk's energy, bore through the collapsing stellar material at speeds incredibly close to the speed of light. As these jets plough through the star, they create an expanding cocoon of hot, shocked gas. When the jets finally burst out of the star's outer layers, they produce the initial prompt emission of gamma rays. This emission is thought to arise from internal shocks within the jet itself, where faster-moving parts of the jet catch up to slower-moving parts, or from magnetic reconnection events within the jet. The energy released in these processes is converted into gamma rays. The sheer power of gamma ray bursts is difficult to comprehend. A typical long GRB can release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifespan. This incredible energy output makes them the most luminous events in the universe since its birth. Their immense power is further amplified by the fact that this energy is not radiated uniformly in all directions. Instead, it is focused into incredibly narrow beams, or jets, like cosmic laser pointers. If a GRB's jet happens to be aimed directly towards Earth, it appears extraordinarily bright, making it detectable across billions of light years. If the same amount of energy were radiated in all directions, the burst would appear far fainter and less threatening. Another source of gamma ray bursts, particularly shorter and sometimes less energetic ones compared to the long cosmological GRBs, are the giant flares from magnetars. As discussed in the magnetic monster topic, magnetars are neutron stars with magnetic fields of quadrillions of Gauss. When these fields undergo extreme rearrangements, or when the star's crust undergoes a starquake, immense amounts of magnetic energy are suddenly released. This energy can manifest as a giant flare of X-rays and gamma rays. While these magnetar flares occur within our own galaxy, and are typically of shorter duration than cosmological long GRBs, their proximity means they can still have significant detectable impacts on Earth's ionosphere, as demonstrated by the SGR 1806-20 event in 2004. These flares demonstrate that even within a single stellar remnant, extraordinary gamma ray events can originate. The physics of GRB emission is complex, involving extreme states of matter and energy. The relativistic jets are composed of a plasma of electrons and positrons, along with protons, all moving at speeds that are 99.9% the speed of light or even higher. As these jets interact with the surrounding interstellar medium, or as different parts of the jet collide, they generate shock waves. These shocks accelerate particles to extreme energies, which then emit radiation across the electromagnetic spectrum. The initial burst of gamma rays is known as the prompt emission. Following this intense flash, there is a longer-lasting afterglow across X-ray, optical, and radio wavelengths. This afterglow is generated as the jet continues to plough into and heat the surrounding gas, and its study provides crucial information about the GRB's environment and the energy it released. Scientists detect gamma ray bursts using dedicated satellites, such as NASA's Swift and Fermi Gamma Ray Space Telescope. These satellites are designed to constantly monitor the sky for these fleeting events. Upon detection of a GRB, rapid alerts are sent to ground-based observatories around the world. This allows astronomers to quickly point their telescopes at the GRB's location to observe the afterglow at longer wavelengths, which fades over hours to days. By studying the afterglow, astronomers can determine the GRB's distance, using its redshift, and its host galaxy, providing vital clues about the type of star that exploded and the environment in which it occurred. This rapid follow-up observation strategy has been instrumental in confirming the collapsar model for long GRBs and has greatly expanded our understanding of these cosmic titans. GRBs are classified primarily by their duration, which serves as a key indicator of their origin. Long GRBs, as described, are linked to the deaths of massive stars. Short GRBs, on the other hand, are thought to arise from the merger of compact objects, a process that also generates gravitational waves. The observation of both gravitational waves and a short GRB from the merger of two neutron stars in 2017 provided strong evidence for this hypothesis, marking a new era of multi-messenger astronomy. Regardless of their origin, both types of GRBs highlight the universe's capacity for unleashing energy on scales that dwarf any terrestrial event, making them objects of both intense scientific fascination and cosmic concern. The true danger of a gamma-ray burst, or GRB, lies not just in its immense energy output, but crucially in its highly focused nature. These are not explosions that radiate uniformly in all directions like a fireworks display. Instead, the energy of a GRB is channeled into incredibly narrow, powerful jets, resembling cosmic laser beams. If one of these beams of death were to be aimed directly at Earth, its destructive potential would be catastrophic, transforming a distant cosmic event into a direct threat to life on our planet. The concept of beaming is fundamental to understanding why GRBs are so dangerous, despite often originating billions of light-years away. When a massive star collapses to form a black hole, or when two neutron stars merge, the immense energy released is not spread out across the entire sphere of space. Instead, the physics of these events, particularly the formation of an accretion disk and the strong magnetic fields, causes the energy to be launched in two opposite, tightly confined cones. These jets are typically very narrow, perhaps only a few degrees wide. This means that only a small fraction of the universe is illuminated by a GRB. For us to detect one, and more importantly to be threatened by one, Earth must lie almost perfectly within one of these narrow beams. The matter within these jets travels at extraordinary, relativistic speeds. This means the particles are moving at velocities extremely close to the speed of light, often 99.9% of the speed of light or even higher. At these speeds, the effects predicted by Albert Einstein's theory of special relativity become significant. One such effect is beaming, where light and particles emitted from a source moving at relativistic speeds are strongly concentrated in the direction of motion. This is similar to how the light from a car's headlamps appears much brighter and more focused when the car is speeding directly towards you. This relativistic beaming effect is what concentrates the immense energy of a GRB into such a tight, powerful beam of death, making it appear incredibly luminous to any observer directly in its path. Once launched, the gamma rays within this beam travel through space at the ultimate cosmic speed limit, the speed of light, approximately 186,000 miles per second. Unlike charged particles, gamma rays are high-energy photons, bundles of light energy, and are not significantly deflected by cosmic magnetic fields or absorbed by the sparse gas and dust in the vast emptiness of intergalactic space. This means that once a GRB beam is emitted, it travels virtually unimpeded across billions of light-years, maintaining its destructive intensity until it interacts with matter. There is no warning time beyond the travel time of light itself. If a GRB aimed at Earth erupts 10,000 light-years away, its gamma rays will arrive 10,000 years later, hitting our planet without any prior detectable signal. The immediate consequences of a direct hit from a GRB beam would be devastating. Upon striking Earth's atmosphere, the high-energy gamma rays would collide with atoms and molecules, stripping electrons from them in a process called ionization. This would create a cascade of high-energy particles and radiation. The most critical immediate effect would be the destruction of Earth's ozone layer. The gamma rays would trigger chemical reactions in the upper atmosphere, forming large amounts of nitrogen oxides. These compounds are highly reactive and would rapidly break down ozone molecules. Within seconds to minutes, a significant portion of the ozone layer, which shields Earth from harmful solar ultraviolet radiation, could be depleted. With the ozone layer severely damaged or destroyed, the planet's surface would be exposed to a deluge of lethal ultraviolet radiation from the sun. This would have catastrophic effects on life. Plankton and other microscopic organisms at the base of the marine food chain, which are highly sensitive to UV radiation, would be severely impacted, leading to widespread collapse of ocean ecosystems. Land plants and animals would suffer from DNA damage, mutations, and direct cellular harm. For humans and other complex life forms, exposure would lead to severe sunburns, increased rates of skin cancer, cataracts, and immune system suppression. The initial blast of gamma rays itself could deliver a significant radiation dose, causing acute radiation sickness and death for any exposed organisms. Beyond biological effects, a direct GRB hit could also generate an electromagnetic pulse, or EMP. This sudden surge of electromagnetic energy could overload and destroy unprotected electronic systems globally, leading to widespread failure of power grids, communication networks, and all modern technology. Satellites in orbit would be particularly vulnerable, likely being rendered inoperable. The overall effect would be a rapid return to a pre-technological era, further complicating any recovery efforts. The kill zone, or danger zone, for a GRB is determined by a combination of its total energy, the narrowness of its beam, and the distance to the target. Scientists estimate that a GRB occurring within a few thousand light-years of Earth and aimed directly at us would be catastrophic. The closer the GRB and the narrower its beam, the more concentrated and destructive the impact. Even a near miss, where the edge of the beam brushes past our solar system, could deliver a significant dose of high-energy radiation, potentially causing long-term climate changes and impacting biological systems, though perhaps not immediately extinguishing all life. Some theories suggest that GRBs might have contributed to past mass extinction events on Earth, though direct evidence remains elusive. The probability of a direct hit from a cosmological GRB on Earth is very low. GRBs are relatively rare events, occurring in a galaxy perhaps once every few hundreds of thousands to millions of years. Furthermore, their beams are very narrow, meaning that only a tiny fraction of the universe is actually in their path. The vastness of space also reduces the chance of a nearby GRB. However, the discovery of magnetaires in our own galaxy, capable of generating powerful but perhaps shorter gamma-ray flares, introduces a closer, albeit less energetic, potential source of concern. While these galactic magnetar flares are generally not considered extinction-level events from their typical observed distances, a powerful superflare from a very close magnetar could still pose a threat to our technology and upper atmosphere. Scientists maintain a constant vigil, monitoring the sky for these powerful bursts. Satellites like Swift and Fermi are specifically designed to detect GRBs and rapidly pinpoint their locations, allowing ground-based telescopes to follow up on their afterglows. This continuous observation helps astronomers understand the distribution of GRBs in the universe and refine their models of these extreme cosmic phenomena, including assessing the remote possibility of a future threat. While the universe is vast and mostly empty, the existence of these beams of death serves as a powerful reminder of the extreme forces at play and the potential for cosmic events to impact life across unimaginable distances. Cosmic rays are not rays in the traditional sense of light or electromagnetic radiation. Instead, they are high-energy particles that travel through space at nearly the speed of light. These particles originate from some of the most energetic and violent phenomena in the universe, making them a continuous and pervasive component of the space environment. Understanding their nature, origins, and interactions is crucial for comprehending their potential impact on spacecraft, astronauts, and planetary atmospheres, including Earth's. The composition of cosmic rays is diverse. Approximately 90% of cosmic rays are protons, which are the nuclei of hydrogen atoms. About 9% are alpha particles, which are the nuclei of helium atoms. The remaining 1% consist of the nuclei of heavier elements, ranging from lithium to iron and beyond, along with a small fraction of electrons and positrons. These particles are fully ionized, meaning they have been stripped of all their electrons, leaving only the bare atomic nuclei. This ionization is a testament to the extreme energies and temperatures involved in their acceleration. Cosmic rays are broadly categorized into two main types based on their origin: galactic cosmic rays and solar cosmic rays. Solar cosmic rays originate from the Sun, primarily from solar flares and coronal mass ejections. These are typically lower in energy compared to galactic cosmic rays, but they can still pose a significant radiation hazard to astronauts and spacecraft, especially during intense solar storms. Galactic cosmic rays, on the other hand, originate from outside our solar system, within our own Milky Way galaxy, and sometimes from even more distant galaxies. These are the focus when discussing the most energetic and potentially dangerous cosmic rays. The primary sources of galactic cosmic rays are thought to be supernova remnants. When a massive star explodes as a supernova, it creates a powerful shockwave that expands rapidly through the interstellar medium. This shockwave acts as a giant particle accelerator. Charged particles, such as protons and atomic nuclei, are caught in the turbulent magnetic fields within the shockwave. They repeatedly cross the shock front, gaining energy with each passage, a process known as Fermi acceleration. This mechanism can accelerate particles to incredibly high energies, far beyond what can be achieved in terrestrial particle accelerators. Other potential sources of galactic cosmic rays include pulsars and magnetars, which can accelerate particles through their rapidly rotating, super-strong magnetic fields, and possibly active galactic nuclei, the extremely luminous centers of some galaxies powered by supermassive black holes. Once accelerated, cosmic rays travel through the vast expanse of interstellar and intergalactic space. Because they are charged particles, their paths are influenced by magnetic fields. The magnetic fields within our galaxy, though relatively weak, are pervasive and can cause cosmic rays to spiral and wander for millions of years before reaching Earth. This means that when we detect a cosmic ray, it is very difficult to trace its exact origin point, as its path has been scrambled by galactic magnetic fields. Only the very highest energy cosmic rays, known as ultra-high energy cosmic rays, are thought to be energetic enough to largely escape the deflecting influence of galactic magnetic fields, potentially allowing astronomers to pinpoint their extragalactic sources. The energy levels of cosmic rays span an enormous range. The lowest energy cosmic rays are similar to particles accelerated in solar flares, while the highest energy cosmic rays carry energies equivalent to a well-hit tennis ball, concentrated into a single subatomic particle. These ultra-high energy cosmic rays are exceedingly rare, but their existence challenges our understanding of cosmic accelerators. When a high-energy cosmic ray strikes Earth's atmosphere, it initiates a cascade of secondary particles, creating an air shower that can be detected by ground-based observatories. This interaction with the atmosphere is crucial for protecting life on the surface. The impact of cosmic rays on space environments is a significant concern for space exploration and the long-term habitability of planets. For astronauts, especially those on long-duration missions beyond the protective bubble of Earth's magnetic field, such as journeys to Mars, exposure to galactic cosmic rays poses a serious health risk. Cosmic rays can penetrate spacecraft shielding and living tissue, causing damage to DNA and cells. This can lead to an increased risk of cancer, cataracts, and degenerative diseases, as well as potential cognitive impairments. Developing effective shielding strategies and understanding the biological effects of long-term cosmic ray exposure are critical challenges for future human spaceflight. Beyond biological effects, cosmic rays can also impact spacecraft electronics. When a high-energy cosmic ray strikes a microchip, it can cause a single event upset, flipping a bit of data, corrupting memory, or even causing a system reset. Over time, repeated bombardment can lead to cumulative damage and degradation of electronic components, potentially causing mission failures. Spacecraft designers must incorporate radiation-hardened electronics and shielding to mitigate these effects. On a planetary scale, cosmic rays can interact with atmospheres, causing ionization and chemical changes. While Earth's thick atmosphere and strong magnetic field provide substantial protection, some cosmic rays still reach the surface. For planets with thinner atmospheres or weaker magnetic fields, the impact can be more pronounced. Continuous bombardment by cosmic rays can contribute to the erosion of planetary atmospheres over geological timescales, slowly stripping away atmospheric gases into space. This process is particularly relevant for planets like Mars, which has a very thin atmosphere and a weak global magnetic field. Cosmic rays also play a role in the chemistry of planetary atmospheres. The ionization caused by cosmic ray interactions can trigger chemical reactions that would not otherwise occur, influencing the composition and temperature profiles of atmospheric layers. For instance, in Earth's atmosphere, cosmic rays contribute to the formation of certain isotopes and can influence cloud formation processes, though the extent of this influence is still a subject of scientific debate. In the interstellar medium, cosmic rays contribute to the ionization and heating of gas clouds, influencing the conditions for star formation. They can also affect the chemical pathways that lead to the formation of complex organic molecules in space. The study of cosmic rays involves a global network of observatories and space-based detectors. Ground-based experiments, such as the Pierre Auger Observatory in Argentina, use arrays of detectors to study the extensive air showers produced by ultra-high-energy cosmic rays. Space-based instruments, like the Alpha Magnetic Spectrometer on the International Space Station and dedicated cosmic ray detectors on satellites, directly measure the composition and energy of cosmic rays before they interact with Earth's atmosphere. These observations provide crucial data for understanding the sources, acceleration mechanisms, and propagation of these enigmatic particles, helping to refine our models of the extreme universe. Gravity is one of the four fundamental forces of nature, responsible for the attraction between any two objects that have mass. It is the force that keeps our feet on the ground, holds planets in orbit around stars, and binds galaxies together. While we experience gravity constantly on Earth, the gravitational pull of a neutron star, particularly a magnetar, is so immense that it defies everyday intuition, representing an extreme manifestation of this fundamental force. This extraordinary gravitational pull is a direct consequence of the star's extreme density, and it has profound effects on nearby objects and even the fabric of space-time itself. To understand the immense gravitational pull of a neutron star, it is essential to recall its defining characteristic, its extreme density. A neutron star packs more mass than our entire Sun into a sphere only about 12 miles in diameter. The strength of gravity depends on two main factors: the mass of the object and the distance from its center. Because a neutron star has a tremendous mass concentrated into an incredibly small volume, objects near its surface are extraordinarily close to its center of mass, leading to an almost unimaginable gravitational force. Consider the surface gravity. On Earth, the acceleration due to gravity is approximately 9.8 meters per second squared. On the surface of the Sun, it is about 28 times stronger than Earth's gravity. However, on the surface of a typical neutron star, the gravitational acceleration can be billions of times stronger than Earth's. If a human were to somehow stand on the surface of a neutron star, the gravitational force would be so overwhelming that they would be instantly flattened to a thickness of mere atoms. Every atom in their body would be subjected to such immense tidal forces that it would be stretched and torn apart. This crushing gravity means that any material falling onto a neutron star hits the surface with incredible energy, releasing powerful bursts of X-rays and gamma rays. The escape velocity from a neutron star is equally extreme. Escape velocity is the minimum speed an object needs to break free from the gravitational pull of a celestial body. From Earth, escape velocity is about 7 miles per second. From the Sun, it is about 380 miles per second. From a neutron star, the escape velocity can be as high as half the speed of light, or even more. This means that anything, whether a particle, a spacecraft, or even light itself, that falls towards a neutron star and crosses a certain boundary will be irrevocably pulled in, accelerating to speeds approaching the speed of light. While a neutron star still has a physical surface, unlike a black hole, the gravitational forces near it are so strong that they blur the distinction. One of the most dramatic consequences of a neutron star's extreme gravity is the phenomenon of tidal forces. Tidal forces arise from the difference in gravitational pull across an extended object. On Earth, the Moon's gravity creates tides in our oceans because the side of Earth closer to the Moon experiences a stronger gravitational pull than the side farther away. For a neutron star, these tidal forces are magnified to an unimaginable degree. If a planet or a smaller star were to approach too close to a neutron star, the gravitational pull on the side facing the neutron star would be vastly stronger than the pull on the side facing away. This differential force would stretch the object into a long, thin stream of material, a process vividly described as spaghettification, before it is completely torn apart and absorbed by the neutron star's gravity. This destructive process is a clear demonstration of the raw power of its gravitational field. Beyond its immediate vicinity, a neutron star's immense gravitational pull also significantly affects the fabric of spacetime itself, as predicted by Albert Einstein's theory of general relativity. According to this theory, mass and energy warp spacetime, and this curvature is what we perceive as gravity. A neutron star with its extreme mass concentrated in a tiny volume creates a profound curvature in the spacetime around it. One observable consequence of this warping is gravitational lensing. Light rays passing near a neutron star are bent by its gravity, much like light passing through a lens. This can cause the images of distant objects to be distorted or even appear multiple times. In the case of a neutron star, the bending of light is so severe that an observer on its surface could theoretically see parts of the star's far side, effectively seeing more than half of its surface at once, as light from the back is bent around to the front. Another relativistic effect of extreme gravity is gravitational time dilation. Time itself slows down in a strong gravitational field. For an observer far away from a neutron star, clocks on the star's surface would appear to tick more slowly than their own. While this effect is negligible in Earth's gravity, it becomes significant near a neutron star, where time can slow down by a measurable amount. This phenomenon has been precisely observed in systems involving pulsars, which are rapidly rotating neutron stars, where the extreme gravity of the pulsar causes subtle but detectable shifts in the timing of its pulses. The gravitational pull of a neutron star also plays a crucial role in its interactions with other celestial bodies, particularly in binary star systems. Many neutron stars are found in binary pairs with a companion star. In such systems, the neutron star's powerful gravity can accrete, or pull in, material from its companion. As gas from the companion star spirals inward towards the neutron star, it forms a superheated accretion disk. The intense friction and compression within this disk heat the gas to millions of degrees Celsius, causing it to emit powerful X-rays. These X-ray binaries are important sources of X-ray radiation in the galaxy, and provide a means for astronomers to study the properties of neutron stars and their extreme gravitational environments. The accretion process can also transfer angular momentum, causing the neutron star to spin up to incredibly rapid rates, forming what are known as millisecond pulses. Furthermore, the gravitational influence of a rogue neutron star, one that has been ejected from its birthplace and travels alone through the galaxy, could potentially disrupt planetary systems it passes close to. While direct collisions are extremely rare due to the vast distances in space, a close gravitational encounter could significantly perturb the orbits of planets, potentially ejecting them from their star system, sending them on a collision course with their host star, or scattering them into the cold emptiness of interstellar space. It could also disturb the outer reservoirs of icy bodies, like the Oort cloud in our solar system, sending a shower of comets towards the inner planets. The study of neutron stars and their extreme gravitational pull provides a unique laboratory for testing the limits of physics, particularly Einstein's theory of general relativity. The precise timing of pulses in binary systems has allowed scientists to observe subtle gravitational effects, such as the decay of orbits due to the emission of gravitational waves, long before gravitational waves were directly detected. The direct detection of gravitational waves from the merger of two neutron stars in 2017 provided unprecedented insights into the properties of matter under such extreme gravitational conditions and confirmed predictions of general relativity in the strongest gravitational fields. These observations are pushing the boundaries of our understanding of gravity and the universe's most compact objects. The universe, while vast and often beautiful, contains phenomena of immense power that can have catastrophic impacts on planets, potentially rendering them uninhabitable or even destroying them. Among these, the most significant threats from a dangerous star like a magnetar or the processes associated with its birth are gamma-ray bursts, or GRBs, and the extreme gravitational and radiative effects of close proximity. Understanding these hypothetical scenarios is crucial for appreciating the fragility of planetary environments in the face of cosmic violence. Let us first consider the impact of a direct hit from a gamma-ray burst. As previously discussed, GRBs are the most powerful explosions in the universe, releasing enormous amounts of energy in tightly focused beams. If such a beam of death were to sweep across a planet like Earth, the consequences would be immediate and devastating. The initial burst of high-energy gamma rays would strike the planet's atmosphere, leading to a rapid and widespread ionization of atmospheric gases. This ionization would trigger a cascade of chemical reactions, particularly involving nitrogen and oxygen. The most critical outcome of these reactions would be the formation of large quantities of nitrogen oxides. These compounds are highly reactive and act as catalysts to break down ozone molecules in the stratosphere. The ozone layer is Earth's natural shield against harmful ultraviolet, or UV, radiation from the sun. Its rapid depletion by a GRB would expose the planet's surface to a sudden and massive increase in solar UV radiation. This would have profound and immediate biological effects. Plankton and other microscopic organisms at the base of the marine food chain are extremely sensitive to UV radiation. Their widespread death would lead to a collapse of ocean ecosystems, impacting all higher forms of marine life. On land, plants would suffer severe damage, leading to widespread crop failures and disruption of terrestrial food chains. Animals, including humans, would experience severe sunburns, DNA damage, increased rates of cancer, and suppression of their immune systems. The direct radiation dose from the GRB itself could also be lethal to exposed organisms, causing acute radiation sickness and death. Beyond the immediate biological effects, a GRB could also trigger an electromagnetic pulse, or EMP. This sudden surge of electromagnetic energy, generated by the interaction of gamma rays with the atmosphere, could induce powerful electrical currents in electronic systems. This would overload and destroy unprotected power grids, communication networks, computers, and all forms of modern electronic technology on a global scale. Satellites in orbit would be particularly vulnerable, likely being rendered inoperable, effectively returning the affected planet to a pre-technological era. The long-term atmospheric changes, including the formation of a persistent brownish haze of nitrogen dioxide, could also lead to global cooling by blocking sunlight, further disrupting climate and ecosystems for years or even decades. Some scientists have speculated that a GRB might have been responsible for the Ordovician-Silurian extinction event on Earth approximately 440 million years ago, which saw a significant loss of marine life, though conclusive evidence remains elusive. Now, let us consider the hypothetical effects of a dangerous star, such as a rogue neutron star or magnetar, passing in close proximity to a planetary system. While a direct collision is extremely unlikely due to the vast distances in space, a close gravitational encounter could still have catastrophic consequences. The immense gravitational pull of the neutron star, as discussed previously, could significantly perturb the orbits of planets within the system. Planets could be pulled out of their stable orbits, leading to a variety of destructive outcomes. They might be ejected entirely from their star system, condemned to wander as rogue planets in the cold emptiness of interstellar space. Alternatively, their orbits could become highly eccentric, leading to extreme temperature variations, or they could be sent on a collision course with their host star or other planets within the system. Beyond direct orbital disruption, a close pass by a massive dense object like a neutron star could also trigger a comet or asteroid shower. In our solar system, the Oort cloud and Kuiper belt are vast reservoirs of icy and rocky bodies located far beyond the orbit of Neptune. The gravitational influence of a passing neutron star could disturb these distant reservoirs, sending a barrage of comets and asteroids hurtling towards the inner planets. Such an event would dramatically increase the frequency of impacts, potentially leading to multiple extinction-level events over a relatively short geological timescale. In the case of a magnetar, its incredibly powerful magnetic field and its propensity for unleashing intense X-ray and gamma-ray flares add another layer of danger. While a magnetar flare is generally less energetic than a cosmological GRB from a collapsing star, its proximity within our own galaxy means its effects could still be significant. A powerful magnetar flare occurring relatively close to a planet could deliver a substantial dose of high-energy radiation. This radiation could strip away a planet's atmosphere over time, especially if the planet lacks a strong protective magnetic field. The continuous bombardment by high-energy particles from the magnetar's magnetosphere could also contribute to atmospheric erosion and disrupt the delicate chemical balance of the atmosphere. Furthermore, the intense magnetic field of a close magnetar could interact directly with a planet's magnetosphere. If a planet has a magnetic field, it would be severely compressed and distorted by the magnetar's field, potentially allowing more harmful radiation to reach the atmosphere. For planets without a strong intrinsic magnetic field, the direct interaction of the magnetar's field with the planet's atmosphere could induce powerful currents, leading to heating and atmospheric loss. The sheer magnetic force could also induce currents in any conductive materials on the planet's surface, potentially disrupting technological infrastructure. The long-term effects of such cosmic events on planetary habitability are profound. Even if a planet is not completely destroyed, the loss of its atmosphere, the sustained bombardment by radiation, or extreme orbital changes could render it completely uninhabitable for complex life. The conditions necessary for life, such as stable temperatures, liquid water, and protection from harmful radiation, would be severely compromised or eliminated. The planet might become a barren, irradiated wasteland, or a frozen, ejected wanderer in the interstellar void. The likelihood of Earth experiencing such a catastrophic event from a dangerous star is, fortunately, very low. Cosmological GRBs are rare, and their narrow beams mean that the chance of a direct hit is statistically small over human timescales. Rogue neutron stars, while they exist, are also rare, and the vast distances between stars in a galaxy make close encounters with planetary systems infrequent. However, the scientific study of these potential impacts is not merely academic. It helps us understand the true fragility of life in the cosmos, the conditions necessary for habitability, and the importance of our planet's natural defences, such as its robust magnetic field and thick atmosphere, which have protected life for billions of years from the constant barrage of less extreme cosmic radiation. It also underscores the dynamic and sometimes violent nature of the universe, where even the most beautiful celestial objects can, under certain circumstances, pose an existential threat. The Sun, planets, moons, asteroids and comets that make up our solar system exist in a delicate gravitational balance, a cosmic dance choreographed over billions of years. While seemingly stable, this intricate arrangement could be profoundly disrupted by the close encounter with, or the extreme radiation from a dangerous star, such as a rogue neutron star or a powerful magnetar. The potential impacts on our solar system, or any similar planetary system, range from subtle orbital shifts to catastrophic dismemberment and sterilization of worlds. One of the most significant threats stems from the immense gravitational pull of a passing rogue neutron star or magnetar. Such an object, possessing the mass of a star but compressed into a city-sized volume, wields an incredibly potent gravitational field. If this rogue star were to pass within a certain critical distance of our solar system, its gravity would begin to significantly perturb the orbits of our planets. The outer planets, like Neptune and Uranus, which are less tightly bound to the Sun's gravity, would be the first to experience noticeable effects. Their orbits could become highly eccentric, meaning they would swing much closer to the Sun at times and much farther away at others, or they could even be completely ejected from the solar system, becoming rogue planets themselves, wandering alone in the vast interstellar void. Even the orbits of the inner, more tightly bound planets, including Earth, would not be entirely immune. A sufficiently close encounter could subtly alter Earth's orbit, perhaps making it more elliptical. This change could lead to more extreme seasonal variations, as the planet moves significantly closer and then farther from the Sun throughout its year. In a more severe scenario, the perturbation could send Earth on a collision course with another planet or even with the Sun itself. While the distances between planets are vast, a major gravitational nudge could destabilize the long-term equilibrium that has ensured our planetary system's stability for over 4.5 billion years. the very delicate orbital resonances that help maintain the stability of planetary motions over millions of years could be broken, leading to unpredictable and chaotic outcomes. Beyond the major planets, the outer reaches of our solar system are home to vast reservoirs of icy and rocky bodies. The Kuiper Belt, beyond Neptune, and the much more distant Oort cloud, a spherical shell of icy objects extending perhaps a quarter of the way to the nearest star. These regions are a relic of the solar system's formation, and their contents are held in a tenuous gravitational balance. A close passage by a rogue neutron star would have a profound effect on these reservoirs. Its gravitational influence could dislodge billions, perhaps trillions of these icy bodies from their orbits, sending a massive shower of comets hurtling towards the inner solar system. This comet storm would dramatically increase the frequency of impacts on Earth and other inner planets, potentially leading to multiple extinction-level events over geological timescales. Such a scenario, while rare, is considered a plausible mechanism for past periods of increased bombardment in our solar system's history. In addition to gravitational disruption, the radiation effects from a dangerous star also pose a significant threat. If a powerful gamma-ray burst, whether from a cosmological event in a distant galaxy or a giant flare from a nearby magnetar, were to be aimed directly at our solar system, its effects would be widespread. The initial burst of gamma rays would sweep through the entire solar system at the speed of light, affecting all planets and moons within its path. For planets with atmospheres, like Earth, the gamma rays would ionize the atmospheric gases, leading to the rapid depletion of the ozone layer, as discussed previously. This would expose planetary surfaces to intense, harmful solar ultraviolet radiation. Even planets without thick atmospheres, like Mars or the Moon, would experience a direct blast of high-energy radiation, which could damage surface materials and pose an immediate lethal threat to any exposed life or technology. For the gas giant planets, like Jupiter and Saturn, the impact of a GRB would be different but still significant. Their massive atmospheres would absorb much of the gamma radiation, leading to intense heating and ionization, potentially triggering dramatic atmospheric storms or chemical changes. The moons of these gas giants, some of which are considered potential abodes for life, would also be exposed. For instance, Europa, Enceladus and Titan, with their subsurface oceans, might be partially shielded by their icy crusts. But surface life, if any, would be severely impacted, and the radiation could still penetrate to a certain depth. The overall radiation environment throughout the solar system would be drastically altered for a considerable period, posing a long-term hazard to space travel and any extraterrestrial colonies. Furthermore, a powerful GRB could generate an electromagnetic pulse that sweeps across the entire solar system. This EMP could induce devastating electrical currents in any conducting materials on planets or spacecraft, leading to widespread damage to electronic systems, power grids, and communication networks across all technological civilizations within its reach. Satellites orbiting any planet would be particularly vulnerable, likely being rendered inoperable. This universal EMP could cripple any spacefaring civilization or any planet with advanced technology, throwing them back into a pre-technological state. The Sun itself, being a star, is robust enough not to be directly destroyed by a distant GRB or the gravitational influence of a passing neutron star, unless it was an extremely close encounter. However, the Sun's activity could potentially be affected. While highly speculative, some theories suggest that extreme external events could, in principle, induce subtle changes in the Sun's convection zone or magnetic dynamo, leading to increased solar flare activity or coronal mass ejections. More plausibly, the sudden influx of high-energy particles from a GRB could temporarily affect the solar wind or the Sun's outer corona. However, the Sun's massive internal inertia and self-regulating fusion processes make it highly resilient to external perturbations on such timescales. The rarity of such extreme events, combined with the immense distances in space, means that the probability of our solar system experiencing a catastrophic encounter with a rogue neutron star or a direct hit from a nearby GRB is extremely low over human timescales. Our solar system resides in a relatively quiet region of the Milky Way, away from the turbulent galactic center and dense star-forming regions where such violent events are more common. However, The existence of such phenomena underscores the dynamic and sometimes perilous nature of the universe. The long-term stability of our solar system is a testament to its current isolated position and the finely tuned balance of gravitational forces. Continuous monitoring of the sky for rogue objects and distant GRBs remains a crucial aspect of planetary defense, however remote the direct threat may be. Star formation zones, often appearing as magnificent nebulae or vast giant molecular clouds, are the stellar nurseries of a galaxy. These regions are typically cold, dense collections of interstellar gas and dust, providing the raw material for new generations of stars and subsequently new planetary systems. However, the very same objects born from the death of massive stars such as supernovae and the neutron stars and magnetars they leave behind can profoundly disrupt these delicate stellar birthplaces, potentially preventing the formation of future stars and planets. Star formation begins when denser pockets within a molecular cloud begin to collapse under their own gravity. As these clumps contract, they heat up, eventually forming protostars surrounded by spinning disks of gas and dust known as protoplanetary disks. It is within these disks that dust grains slowly accrete, colliding and sticking together to form planetesimals, which eventually grow into planets. This entire process relies on the molecular cloud remaining relatively undisturbed for millions of years, allowing gravity to slowly work its magic. The most direct way a dangerous star disrupts star formation zones is through the violent aftermath of a supernova explosion. When a massive star reaches the end of its life and explodes as a supernova, it releases an enormous amount of energy in the form of a powerful shockwave. As this shockwave propagates through the surrounding interstellar medium, it encounters existing molecular clouds. The interaction can have dual effects. In some instances, the shockwave can act as a catalyst, compressing regions within the cloud to the point where they become gravitationally unstable and begin to collapse, thus triggering new star formation. This is one of the proposed mechanisms for propagating star formation through a galactic arm. However, the destructive effects of a supernova shockwave are often more pronounced, particularly for smaller, more fragile molecular clouds or existing protostars. The intense blast wave can simply rip apart these clouds, dispersing their gas and dust into the vastness of space. This process, known as photoevaporation or ablation, prevents the material from ever accumulating enough mass to form stars. Any nascent protostars or young protoplanetary disks within the immediate vicinity of the supernova would also be severely disrupted or destroyed. The shockwave would strip away their outer envelopes, disperse their disks, or even fling them out of the nebula entirely. The iconic Pillars of Creation in the Eagle Nebula, for example, are believed to be dense pockets of gas and dust being slowly eroded by the intense radiation and stellar winds from nearby massive stars, a process that would be dramatically accelerated and intensified by a supernova. Beyond the mechanical force of the shockwave, the intense radiation emitted by a supernova also plays a critical role in disruption. A supernova emits vast quantities of high-energy radiation, including ultraviolet, X-rays, and gamma rays. This radiation can penetrate deeply into molecular clouds, ionizing the gas and dust. Ionized gas, being electrically charged, is more susceptible to magnetic fields and less likely to cool efficiently. Cooling is a crucial step in star formation, as it allows the cloud to lose thermal pressure and continue its gravitational collapse. By heating and ionizing the gas, the supernova's radiation can effectively prevent further collapse, halting star formation in that region. The intense heat would also increase the internal pressure of the cloud, causing it to expand and dissipate rather than contract. Furthermore, supernovae, and particularly magnetar flares, contribute to the presence of cosmic rays. These high-energy particles can penetrate molecular clouds, causing further ionization and heating. While less dramatic than a direct shockwave or a GRB, a continuous flux of cosmic rays can slowly erode molecular clouds over longer timescales, contributing to their overall dissipation and reducing the amount of raw material available for new stars. The strong magnetic fields of magnetars, which are born from supernovae, can also influence the magnetic field structure within a nebula. Magnetic fields within molecular clouds are crucial for supporting the cloud against collapse in some regions and guiding the flow of gas in others. A sudden, powerful magnetic disturbance from a nearby magnetaire could potentially disrupt this delicate magnetic equilibrium, hindering or altering the star formation process. The consequences for planet formation within these disrupted zones are equally severe. If a molecular cloud is dispersed by a supernova or intensely radiated by a GRB, there will simply be insufficient gas and dust to form the protoplanetary disks that are the birthplaces of planets. Even if protoplanetary disks have already formed, they are highly vulnerable to the harsh environment created by a supernova or a powerful magnetar flare. The intense radiation and stellar winds could rapidly evaporate the gas and dust from these disks, essentially sterilizing them before planets have a chance to grow. Without enough material, the accretion process that builds planetesimals and then planets cannot proceed. Any young, forming planets might be subjected to extreme radiation levels, hindering the development of any nascent life or sterilizing them entirely. The chemical composition of star-forming regions can also be affected. While supernovae are crucial for enriching the galaxy with heavy elements, which are necessary for rocky planet formation, the immediate destructive effects on a specific cloud can be localized. The shock waves can alter the chemical pathways within the cloud, destroying complex organic molecules that might be precursors to life. The dust grains, essential for the initial steps of planet formation, can also be shattered or evaporated by the intense energy, further compromising the ability of the region to form planets. Galaxies, particularly spiral galaxies like our own Milky Way, are characterized by their majestic, sweeping spiral arms. These arms are not rigid, unchanging structures, but rather dynamic regions where most of the galaxy's gas, dust, and young, bright stars reside. They are sites of active star formation, often glowing brightly due to the presence of massive, short-lived stars. The destructive power of a dangerous star, whether it be a supernova, a magnetar, or a rogue neutron star, can profoundly affect these galactic arms, influencing their structure, gas content, and ongoing stellar activity. Galactic spiral arms are typically understood through the density wave theory. This theory proposes that the arms are not material structures where individual stars and gas clouds remain fixed, but rather areas of higher density that propagate through the galactic disk, similar to a traffic jam on a highway. As gas and dust clouds enter these density waves, they are compressed, triggering gravitational collapse and leading to bursts of star formation. This explains why the arms appear bright with young blue stars and nebulae, as these massive stars are short-lived and only survive within the arm where they formed. The most dramatic local impact on a galactic arm comes from supernovae, the explosive deaths of massive stars. Since massive stars are predominantly born within the spiral arms, supernovae are also most frequent there. A single supernova explosion, while powerful, typically causes localized disruption. However, in regions of intense star formation within an arm, multiple supernovae can occur in close succession, creating much larger and more significant disturbances. The combined shock waves and stellar winds from these multiple explosions can clear out vast regions of gas and dust, forming superbubbles or supercavities within the galactic arm. These gigantic bubbles, sometimes hundreds of light years across, push the interstellar medium out of the arm, creating less dense regions where star formation is temporarily inhibited. These powerful events also contribute to driving galactic winds. As gas is heated and propelled out of the galactic disk by repeated supernovae in a spiral arm, it can create a hot, ionized outflow that extends vertically, away from the galactic plane. This process expels matter into the galactic halo, fundamentally altering the distribution of gas within the galaxy and potentially affecting the long-term cycle of star formation in the arm by removing raw materials. The turbulent energy injected by supernovae also stirs the interstellar medium within the arm, creating complex patterns of gas flows and magnetic fields, which can both trigger and suppress local star formation in different regions. A magnetar, being born from a supernova, can exert its own unique influence on a galactic arm. While the direct magnetic field effects of a single magnetar are localized, a powerful magnetar giant flare, like the one observed from SGR 1806-20, can send a pulse of high-energy radiation across a significant portion of a galactic arm. If such a flare were to occur relatively close to a populated region of an arm, the intense burst of X-rays and gamma rays could sterilize planets or cause widespread atmospheric damage across hundreds or even thousands of light-years, impacting any life forms within the beam's path. While not destroying the arm itself, such an event could render vast regions within it inhospitable for life, effectively creating a dead zone for biological evolution. Furthermore, the high-energy particles or cosmic rays ejected from supernovae and magnetars contribute to the overall radiation environment within the galactic arms. These particles, travelling at nearly the speed of light, permeate the interstellar medium, interacting with gas and dust. While this can contribute to heating and ionization, potentially disrupting some star-forming regions as discussed in the previous topic, their primary effect on the large-scale structure of galactic arms is indirect. They are a product of the energetic processes within the arms, rather than a primary driver of arm evolution. Rogue neutron stars, those ejected from their birthplaces at high velocities, represent a different kind of impact on galactic arms. These objects can travel across the galactic disk, cutting across spiral arms. While direct stellar collisions are incredibly rare due to the vast distances between stars, the gravitational influence of a passing rogue neutron star can cause localized perturbations. If a rogue neutron star passes through a particularly dense region of gas and dust within a spiral arm, its gravity could induce local gravitational instabilities, potentially triggering small pockets of star formation. Conversely, if it passes near existing stellar clusters or protostars, its gravitational pull could disrupt those formations, potentially ejecting individual stars or newly forming planetary systems from the arm. These effects, however, are typically localized and do not significantly alter the large-scale structure or dynamics of the entire galactic arm. The overall effect of these dangerous stars on galactic arms is a complex interplay of destruction and creation. Supernovae, while destructive to individual clouds, are also essential for the ongoing cycle of star formation in the arms by compressing gas and creating new generations of stars. They are also the primary mechanism by which heavy elements, forged in their fiery cores and explosive deaths, are distributed throughout the galaxy, enriching the interstellar medium and making rocky planet formation possible within the arms. Without supernovae, the spiral arms would eventually run out of the raw materials for new stars and planets. However, the localized violence of these events ensures that galactic arms are dynamic and turbulent environments. They are not static regions, but constantly evolving structures, shaped by the birth and death of massive stars. While a single dangerous star or a cluster of supernovae will not destroy a galactic arm, which is a massive gravitationally bound structure of billions of stars and vast amounts of gas, they contribute to its internal chaos, influencing where and when new stars form, how gas is distributed, and the overall habitability of planetary systems within those regions. The presence of these powerful and sometimes destructive objects is an intrinsic part of the energetic and constantly evolving nature of the spiral arms of a galaxy. The universe is a vast interconnected system where monumental cosmic events do not occur in isolation. The initial destruction caused by a dangerous star, whether it is the explosive death of a massive star in a supernova or a powerful giant flare from a magnetar, can trigger a complex chain reaction of events, spreading effects far beyond the immediate blast zone and across wider regions of a galaxy. This ripple effect can reshape gas clouds, influence stellar nurseries, and even alter the habitability of distant planetary systems over long stretches of cosmic time. The most direct and immediate ripple from a supernova is its shockwave. When a star explodes, it releases an immense amount of energy that propels its outer layers outward at thousands of miles per second, creating a rapidly expanding shell of superheated gas and a powerful blast wave. As this shockwave travels through the interstellar medium, the sparse gas and dust between stars, it interacts with everything in its path. In some instances, this interaction can be constructive. If the shockwave encounters a diffuse region within a molecular cloud, the compression it causes can be sufficient to overcome the cloud's internal pressure and trigger gravitational collapse, initiating the formation of new stars. This is one of the proposed mechanisms by which star formation propagates through a galactic arm, with one generation of massive stars exploding and prompting the birth of the next. However, the destructive aspects of this shockwave are also profound. If the blast wave hits smaller, more fragile molecular clouds or regions that are just beginning to collapse into protostars, it can disperse them entirely. The intense pressure and velocity of the shockwave can rip apart these delicate structures, scattering their gas and dust into space, and preventing the formation of stars in those specific locations. Any existing protoplanetary disks, the swirling nurseries of gas and dust from which planets form around young stars, would also be highly vulnerable. The shockwave could strip away their outer layers, effectively sterilizing the disk and robbing it of the material necessary to form or grow planets. The intense heat generated by the shockwave, reaching millions of degrees, also expands and ionizes the gas in its path, making it less likely to cool and collapse into new stars. Beyond the shockwave, the initial burst of radiation from a supernova or a giant magnetar flare creates a powerful radiation field that ripples outward at the speed of light. This broad-spectrum radiation, encompassing ultraviolet, X-rays, and gamma rays, can ionize vast volumes of interstellar gas, creating immense bubbles of glowing plasma known as H2 regions or supernova remnants. These regions can grow for thousands of years, pushing against the surrounding interstellar medium and reshaping the gas distribution across significant portions of a galactic arm. The radiation can also photoevaporate, or boil away, the gas and dust from the surfaces of molecular clouds and protoplanetary disks, further contributing to their dispersal. Another critical component of the ripple effect is the acceleration of cosmic rays. Supernovae are considered the primary accelerators of galactic cosmic rays, high-energy charged particles that travel through space at nearly the speed of light. While the direct effects of cosmic rays are less dramatic than a shockwave or a gamma-ray burst, they represent a long-term, pervasive radiation hazard that propagates across vast distances. These cosmic rays can permeate large regions of a galaxy, affecting the radiation background for millions of years. Any planets within these regions would experience a continuous bombardment, leading to slow but cumulative effects like atmospheric erosion over geological timescales, subtle chemical changes in the atmosphere, and long-term radiation exposure for any life forms. On a larger galactic scale, the cumulative effect of multiple supernovae and magnetar flares within a star-forming region can lead to even more significant ripples. If many massive stars explode in a concentrated area, their combined energy can create vast superbubbles that are hundreds or even thousands of light-years across. These superbubbles can expand so forcefully that they punch through the galactic disk, expelling gas into the galactic halo, the diffuse region above and below the main disk. This process, known as a galactic fountain or galactic wind, recycles gas by sending it up into the halo, where it eventually cools and falls back down into the disk, but it also fundamentally alters the distribution and dynamics of gas within a galaxy, impacting future star formation in those regions. Furthermore, the initial destructive event can lead to a chain reaction of star formation and subsequent supernova. The compression caused by a supernova shockwave can trigger the collapse of nearby gas clouds, leading to the birth of a new generation of massive stars. These newly formed massive stars, being short-lived, will then quickly explode as supernovae themselves, propagating the cycle of shockwaves and disruption. This self-propagating star formation can create complex patterns of activity within galactic arms, constantly reshaping the environment and driving the evolution of the galaxy's stellar populations and gas distribution. The magnetic fields within a galactic arm can also be affected by these powerful events. Supernovae can inject turbulent energy into the magnetic fields, causing them to twist and tangle, which can in turn influence the stability and collapse of gas clouds. The ripple effect also extends to the chemical enrichment of the galaxy. While the immediate localized effects of a supernova can be disruptive, the explosion is also the primary mechanism for dispersing heavy elements forged in the star's core, and during the explosion itself, such as iron, gold, and uranium, into the interstellar medium. These elements are then incorporated into new generations of stars and planets. Thus, the ripple includes a fundamental process of cosmic recycling and evolution, where the destruction of one star provides the building blocks for countless others. However, The localized over-enrichment of certain regions could also subtly alter the conditions for subsequent star formation, leading to variations in the elemental composition of newly formed planetary systems. Finally, the ripples from a dangerous star can have long-term consequences for the habitability of regions within a galaxy. While the direct hit from a GRB might sterilize a single planet, the propagation of shock waves, radiation fields, and cosmic rays can collectively raise the ambient radiation background across vast areas of a galactic arm. This increased radiation can pose a continuous threat to any life that might evolve on planets within these regions, requiring more robust planetary defenses or limiting the types of life that can survive. The cumulative effect of these ripples can shift the overall habitability landscape of a galaxy, defining regions that are more or less conducive to the sustained evolution of complex life. These chain reactions, unfolding over millions of years, demonstrate how the death of a single star can profoundly influence the future of a galaxy. Detecting the rare and often elusive dangerous stars, particularly isolated neutron stars and magnetars, poses a significant challenge for astronomers. These objects are incredibly small, often only 12 miles across, and typically do not emit much visible light, making them nearly invisible against the vast backdrop of space. Therefore, astronomers rely on a variety of sophisticated techniques and telescopes that observe across the electromagnetic spectrum, not just visible light, to indirectly identify their presence and study their extreme properties. One of the most common ways to find neutron stars is through their manifestation as pulsars. Pulsars are rapidly rotating neutron stars that emit highly collimated beams of radio waves from their magnetic poles. If one of these beams sweeps across Earth as the neutron star spins, like a lighthouse beacon, we detect it as a regular pulse of radio emission. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell and Anthony Hewish revolutionized astronomy, providing the first direct evidence for the existence of neutron stars. Astronomers use large radio telescopes, such as the Arecibo Observatory, the Parkes Observatory, and the Future Square Kilometre Array, to scan the sky for these characteristic radio pulses. The precise timing of these pulses allows astronomers to determine the neutron star's spin rate, its location, and even infer the presence of companion stars or planets orbiting it. Pulsars are incredibly stable clocks, and their timing deviations can reveal subtle gravitational effects, even confirming predictions of Einstein's theory of general relativity. Another crucial method for finding neutron stars is through the detection of X-rays. Many neutron stars are found in binary systems, where they orbit a companion star. If the companion star is close enough, the neutron star's immense gravity can pull gas from its outer layers. This gas spirals inward, forming a superheated accretion disk around the neutron star. As the gas in this disk spirals closer to the neutron star, it is heated to millions of degrees Celsius due to friction and compression, causing it to emit powerful X-rays. These systems are known as X-ray binaries, and they are among the brightest X-ray sources in the galaxy. Astronomers use space-based X-ray telescopes like the Chandra X-ray Observatory and XMM Newton to detect these emissions. By studying the X-ray light curves, spectra, and variations, astronomers can infer the mass of the neutron star, its accretion rate, and the properties of the companion star. Supernova remnants also serve as important signposts for locating neutron stars. A supernova explosion leaves behind an expanding shell of gas and dust. Often, a compact object, either a neutron star or a black hole, resides at the center of this remnant. Astronomers use optical, radio, and X-ray telescopes to observe these remnants. For example, the Crab Nebula is a well-known supernova remnant from an explosion observed in the year 1054, and at its heart lies a rapidly spinning pulsar, the Crab Pulsar, which is a neutron star. Observing the expanding remnant, its characteristic emission across various wavelengths, and looking for a central compact object are key steps in confirming the presence of a newly formed neutron star. Magnetars, a specific type of dangerous neutron star, are primarily identified by their unique X-ray and gamma-ray bursting activity. Unlike typical pulsars that emit regular radio pulses, magnetars often show irregular bursts of X-rays and gamma rays as well as a persistent X-ray emission that is much brighter than what their rotational energy alone could power. These bursts, stemming from extreme magnetic field stresses and starquakes, are the primary signals astronomers look for. Dedicated gamma-ray telescopes and satellites, such as NASA's Fermi Gamma-Ray Space Telescope and the SWIFT satellite, are designed to continuously monitor the sky for these transient high-energy events. When a burst is detected, rapid alerts are sent to ground-based observatories, which then quickly point their optical and radio telescopes to search for any fading afterglow or persistent emission, allowing for precise localization and further study of the magnetar. The direct detection of gravitational waves, a groundbreaking achievement in astrophysics, has also opened a new window into finding and studying neutron stars. In 2017, the LIGO and Virgo gravitational wave observatories detected gravitational waves emanating from the merger of two neutron stars. This event, known as GW 1770817, not only confirmed the existence of binary neutron star systems, but also provided a direct observation of the extreme gravitational dynamics associated with these compact objects. Following the gravitational wave detection, astronomers observed a short gamma-ray burst and a subsequent afterglow across the electromagnetic spectrum, confirming that neutron star mergers are a source of both gravitational waves and short GRBs. This multi-messenger astronomy approach provides unprecedented insights into the properties of neutron stars and the processes that create the most extreme phenomena in the universe. The challenges in finding isolated neutron stars that are not pulsars or part of X-ray binaries are significant. Because they are so small and do not emit much light, they are incredibly faint and difficult to distinguish from background stars. Astronomers attempt to detect them through their faint X-ray emission, from residual heat or very weak accretion of interstellar gas. Another proposed method is through gravitational microlensing, where a passing neutron star temporarily brightens the light of a more distant background star as its gravity bends the light rays. While theoretically possible, these observations are extremely difficult and rare. Similarly, detecting rogue neutron stars, those ejected from their original systems at high velocities, requires meticulous long-term observations to track their proper motion across the sky, which distinguishes them from stationary background objects. X-ray astronomy provides an unparalleled vision into the universe's most extreme and energetic phenomena, making it an indispensable tool for detecting and studying dangerous stars like neutron stars and magnetars. Unlike visible light, which reveals stars burning quietly or nebulae glowing softly, X-rays are emitted by matter at millions of degrees Celsius, or by highly accelerated particles interacting with strong magnetic fields. Since Earth's atmosphere completely absorbs X-rays, X-ray telescopes must be placed in space, offering a unique window into the violent and high-energy cosmos that would otherwise remain hidden. The primary reason X-rays are so crucial for observing neutron stars and magnetars is that these objects, despite their immense mass, are incredibly small and thus do not emit much visible light. However, their extreme conditions, whether it is the residual heat from their formation, the superheated gas accreting onto them, or the energy released by their incredibly powerful magnetic fields, generate prolific X-ray emission. This X-ray signature serves as a beacon, revealing their presence and providing vital clues about their physical properties. One significant source of X-rays from neutron stars comes from X-ray binaries. In these systems, a neutron star orbits a companion star, and its immense gravity pulls gas from the companion. As this gas spirals inward towards the neutron star, it forms an accretion disk. The intense friction and compression within this disk heat the gas to temperatures ranging from millions to hundreds of millions of degrees Celsius. At these extreme temperatures, the gas emits profusely in the X-ray part of the spectrum. X-ray telescopes can detect these emissions, allowing astronomers to study the accretion process, estimate the mass of the neutron star, and observe phenomena like jets of high-energy particles being launched from the system. The specific patterns of X-ray emission and variability provide detailed information about the dynamics of matter in the immediate vicinity of these ultra-compact objects. Magnetars are particularly bright in X-rays, often having a persistent X-ray emission that is much higher than what would be expected from their rotational energy alone. This persistent X-ray luminosity is believed to be powered by the slow decay and dissipation of their incredibly powerful magnetic fields. More dramatically, magnetars are known for their spectacular X-ray and gamma-ray flares, which are sudden, intense bursts of high-energy radiation. These flares are thought to be caused by starquakes in the magnetar's crust, or sudden rearrangements of its magnetic field lines, releasing enormous amounts of stored magnetic energy. X-ray telescopes are instrumental in detecting these bursts and studying their energy spectra and durations, providing critical insights into the physics of extreme magnetic fields and the internal structure of these objects. The NICIA, or Neutron Star Interior Composition Explorer, mission on the International Space Station, for example, uses X-ray timing observations to study the masses, radii, and internal composition of neutron stars with unprecedented precision by observing X-ray hotspots on their surfaces, supernova remnants. The expanding shells of gas left behind after a massive star's explosion are also strong X-ray emitters. As the supernova shockwave expands, it heats the surrounding interstellar gas to millions of degrees, causing it to glow brightly in X-rays. X-ray telescopes allow astronomers to map the structure of these remnants, study their evolution, and investigate the chemical elements dispersed by the explosion. Often, a central neutron star, the remnant of the original explosion, can be found within these X-ray glowing clouds, detectable by its own X-ray emission or by its characteristic pulsations. Pulsar wind nebulae, which are created by the energetic winds emanating from rapidly spinning pulsars interacting with surrounding magnetic fields, also emit strongly in X-rays, revealing the presence of highly energetic particles and intense magnetic interactions. The technology behind X-ray telescopes is vastly different from that of optical telescopes, because X-rays, being much more energetic than visible light, cannot be reflected in the same way. Instead of normal incidence mirrors, X-ray telescopes use a technique called grazing incidence. This involves a series of nested, highly polished cylindrical or conical mirrors. X-rays strike these mirrors at very shallow angles, typically less than a few degrees, and are gently reflected towards a detector. Each mirror reflects only a small fraction of the X-rays, but by nesting many such mirrors inside each other, a significant portion of the X-rays can be focused onto a detector. These detectors typically use charge-coupled devices, or CCDs, similar to those in digital cameras, or more advanced microcalorimeters, to capture the X-ray photons and measure their energy and position. Major X-ray observatories in space, such as the Chandra X-ray Observatory, XMM Newton and NICIA, have revolutionized our understanding of neutron stars and magnetars. Chandra, launched by NASA, is renowned for its incredibly sharp X-ray images, allowing astronomers to resolve fine details in supernova remnants and accretion disks around neutron stars. XMM Newton, operated by the European Space Agency, boasts a large collecting area, making it highly sensitive to faint X-ray sources and providing excellent spectral information. The Swift satellite, primarily a gamma-ray burst mission, also carries an X-ray telescope that is crucial for rapidly detecting and studying the X-ray afterglows that follow the initial gamma-ray burst, helping to pinpoint their location and understand their physics. What X-ray observations tell us about dangerous stars is multifaceted. They allow us to measure the surface temperatures of cooling neutron stars, providing insights into their internal structure and cooling processes. In X-ray binaries, they reveal the dynamics of matter spiraling onto the neutron star, allowing for precise measurements of the star's mass and helping to constrain the elusive equation of state for super-dense matter inside them. For magnetaires, X-ray data provides direct evidence of their extreme magnetic fields through the persistent X-ray emission and the spectacular flares. The timing of X-ray pulses from these objects helps astronomers track their spin rates and detect glitches, sudden changes in spin that can reveal information about the star's interior. Ultimately, X-ray vision is an indispensable tool, allowing humanity to peer into the universe's most violent and magnetically extreme environments, revealing the hidden lives of dangerous stars. Radio signals provide astronomers with an extraordinary way to listen to the universe, revealing objects and phenomena that are invisible to our eyes. For dangerous stars like neutron stars, particularly the class known as pulsars, radio astronomy is a fundamental tool for detection and understanding. These incredibly dense stellar remnants often emit highly regular pulses of radio waves, acting as cosmic lighthouses that broadcast their presence across vast stretches of space. Radio waves are a type of electromagnetic radiation, just like visible light, X-rays, or gamma rays. However, they have much longer wavelengths and lower frequencies. This means they are not absorbed by Earth's atmosphere, allowing ground-based radio telescopes to observe them directly. A radio telescope consists of a large dish-shaped antenna that collects these faint radio waves. The dish acts like a giant funnel, focusing the radio signals onto a receiver at its focal point. This receiver converts the radio waves into electrical signals, which are then processed by powerful computers. These computers are essential for sifting through vast amounts of data, searching for the subtle periodic patterns that indicate the presence of a pulsar. Often, multiple radio dishes are linked together to form an interferometer, like the Very Large Array in New Mexico or the Future Square Kilometre Array, which can achieve much higher resolution and sensitivity than a single dish. The emission of radio waves from a pulsar is a unique phenomenon. A pulsar is a rapidly spinning neutron star with an incredibly strong magnetic field. This magnetic field is not perfectly aligned with the star's rotation axis. As the neutron star spins, charged particles, primarily electrons and positrons, are accelerated to nearly the speed of light along the star's magnetic field lines, particularly near the magnetic poles. These accelerated particles emit radiation in a narrow cone-shaped beam that streams out into space. As the neutron star rotates, this beam sweeps across the cosmos, much like the beam from a lighthouse. If Earth happens to lie in the path of this sweeping beam, we observe a brief, sharp pulse of radio waves with each rotation. This lighthouse model explains the remarkable regularity of pulsar signals. The discovery of the first pulsar in 1967 by astronomer Jocelyn Bell Burnell and her supervisor Anthony Hewish was a groundbreaking moment in astronomy. Initially, the incredibly precise and regular signals, nicknamed LGM-1 for Little Green Men, one due to their mysterious origin, led to speculation about extraterrestrial intelligence. However, it was soon realized that these signals were emanating from a rapidly rotating, highly magnetized neutron star, confirming the existence of these exotic objects that had only been theorized just a few decades prior. Since then, thousands of pulsars have been discovered across our Milky Way galaxy and beyond. Radio telescopes reveal several key properties of pulsars, providing invaluable data about these dangerous stars. The most fundamental piece of information is the pulsar's spin period, which is the time it takes for the neutron star to complete one rotation. These periods can range from many seconds to just a few milliseconds. The precision of these periods is astonishing, often more stable than the best atomic clocks on Earth. This extreme stability makes pulsars natural cosmic clocks, useful for a variety of scientific experiments. By monitoring the spin period over time, astronomers can also measure the pulsar's spin-down rate, which is the very gradual slowing down of its rotation. This spin-down is caused by the energy carried away by the pulsar's magnetic field and its radiation. The spin-down rate provides crucial information about the strength of the pulsar's magnetic field and its age. A faster spin-down indicates a stronger magnetic field and a younger age. Conversely, millisecond pulsars, which spin hundreds of times per second, have extremely slow spin-down rates, indicating much weaker magnetic fields and much older ages, often thought to have been spun up by accreting matter from a companion star in a binary system. Radio signals from pulsars also provide information about the interstellar medium, the gas and dust between stars. As radio waves travel through space, they interact with free electrons in the interstellar plasma. This interaction causes longer wavelength radio waves to travel slightly slower than shorter wavelength radio waves, a phenomenon known as dispersion. By measuring the delay and arrival times of a pulsar's pulse at different radio frequencies, astronomers can calculate the dispersion measure, or DM, of the signal. Since the electron density in the interstellar medium is relatively well known, the DM provides a good estimate of the distance to the pulsar. Deviations from the perfect regularity of pulsar pulses, known as timing variations, are particularly rich sources of information. A sudden, small increase in a pulsar's spin rate, called a glitch, can reveal details about the neutron star's internal structure. Glitches are thought to be caused by sudden rearrangements within the neutron star's interior, possibly involving the superfluid neutron component of its core. If a pulsar is part of a binary system, its orbital motion around a companion star causes tiny Doppler shifts in the arrival times of its pulses. By meticulously tracking these shifts, astronomers can precisely determine the orbital parameters of the binary system, including the masses of both stars. This method was famously used to discover the first exoplanets, orbiting a pulsar named PSR B 1257+12 in 1992. Perhaps most significantly, the study of binary pulsars has provided some of the strongest evidence for Einstein's theory of general relativity and the existence of gravitational waves. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other. The extreme gravitational environment of this system causes its orbit to decay due to the emission of gravitational waves, tiny ripples in space-time. By precisely measuring this orbital decay through radio timing, astronomers confirmed Einstein's predictions for gravitational wave emission years before gravitational waves were directly detected by instruments like LIGO. Finally, the polarization of radio waves, which refers to the orientation of their electric and magnetic fields, provides additional clues about the pulsar's magnetic field geometry and the emission mechanism itself. By analysing how the polarization changes as the pulsar rotates, astronomers can build detailed models of the magnetic field structure around these extreme objects. While not all radio pulsars are considered dangerous in the sense of directly unleashing destructive power like magnetar flares, their study through radio signals provides fundamental insights into the physics of neutron stars, their extreme density, gravity, and magnetic fields, which are indeed integral to understanding the most powerful and potentially threatening objects in the cosmos. Some magnetars, the most dangerous type of neutron star, also exhibit radio pulsations, and their radio emissions can be highly variable and linked to their bursting activity. Astronomers investigating dangerous stars and their extreme phenomena gather a vast array of data using various telescopes and detectors across the entire electromagnetic spectrum and even beyond with gravitational waves. This systematic collection of information is fundamental to understanding the nature of these cosmic objects, how they behave, and when they might unleash their destructive power. The types of data collected are diverse, each providing unique insights into the physics governing these extreme environments. One of the most crucial types of data collected, especially for pulsars and magnetars, is timing data. For pulsars, this involves meticulously measuring the arrival times of their radio pulses. These measurements are incredibly precise, often down to microseconds, and are used to determine the star's spin period, the exact time it takes to complete one rotation. By tracking these periods over long time scales, astronomers can measure the spin-down rate, which is the very gradual slowing down of the pulsar's rotation. This spin-down rate provides direct information about the rate at which the pulsar is losing energy, primarily due to its magnetic field, offering clues about the strength of the magnetic field and the pulsar's age. For magnetars, similar precise timing of their X-ray and gamma-ray pulsations, as well as the arrival times of individual photons during flares, is essential to understand their rotational properties and how they respond to magnetic stress. Timing data also reveals specific, often sudden, events like glitches. A glitch is a sudden, small increase in a pulsar's spin rate, observed as a momentary deviation from its steady spin down. These glitches are thought to be caused by sudden internal rearrangements within the neutron star, possibly involving the transfer of angular momentum from a rapidly rotating superfluid interior to the solid crust. Recording the precise timing and magnitude of these glitches provides unique probes into the internal structure of these incredibly dense objects. In binary systems, timing variations due to the pulsar's orbital motion allow astronomers to precisely measure orbital parameters such as the period, eccentricity, and inclination of the orbit, which in turn are used to calculate the masses of the neutron star and its companion, a vital piece of information for understanding stellar evolution models. Another critical category of data is spectral data. This involves measuring how much radiation an object emits at different wavelengths or energies, from radio waves to gamma rays. Spectral data reveals the physical conditions of the emitting region. For instance, X-ray spectra from neutron stars can indicate their surface temperature, which reflects their cooling rate after formation. In X-ray binaries, the spectrum of X-rays emitted from the accretion disk tells astronomers about the temperature, density, and ionization state of the gas spiraling onto the neutron star. Specific spectral features, like absorption or emission lines, can reveal the chemical composition of the surrounding gas in supernova remnants or accretion disks. For magnetaires, features in their X-ray spectra, such as cyclotron resonance features, can directly measure the strength of their incredibly powerful magnetic fields, providing direct evidence for their defining characteristic. Imaging data, obtained primarily from optical, X-ray, and radio telescopes, allows astronomers to visualize these objects and their environments. High-resolution X-ray images from observatories like Chandra can pinpoint the exact location of a neutron star within a supernova remnant or in a distant galaxy, helping to identify its host galaxy. These images can also reveal the morphology of supernova remnants, the structure of pulsar wind nebulae, and the geometry of accretion disks around neutron stars in binary systems. By observing the position of a neutron star over many years, astronomers can measure its proper motion, its movement across the sky, which is crucial for identifying rogue neutron stars that are travelling at high velocities through the galaxy. Brightness changes over time, often represented in light curves, provide dynamic insights into the behaviour of dangerous stars. Astronomers record the intensity of radiation across various wavelengths to observe how it varies. For magnetars, detailed light curves of their flares and superflares, which can last from milliseconds to minutes, capture the rapid increase and decay of their immense energy output. These light curves provide information about the energy release mechanism and the physics of magnetic reconnection. For gamma-ray bursts, the light curves of both the initial prompt gamma-ray emission and the longer-lasting X-ray, optical and radio afterglows are meticulously studied. The shape and decay rate of the afterglow light curve provide information about the energy of the explosion, the properties of the relativistic jets, and the density of the surrounding interstellar medium. In X-ray binaries, variations in brightness can indicate instabilities in the accretion disk or changes in the accretion rate onto the neutron star. Polarization data, which measures the orientation of the electromagnetic waves, offers another layer of information. For radio pulsars, the polarization of their radio pulses provides clues about the geometry of their magnetic fields and the mechanism by which the radio waves are generated. In X-ray astronomy, measuring X-ray polarization from neutron stars or magnetaires can provide insights into the structure of their magnetic fields and the processes that accelerate particles to high energies. A relatively new but profoundly important type of data is gravitational wave data. The direct detection of gravitational waves from the merger of two neutron stars by observatories like LIGO and Virgo provides entirely new information about these extreme objects. The precise waveform of the gravitational waves can reveal the masses and spins of the merging neutron stars, and critically, it can constrain the equation of state of neutron star matter, which describes how matter behaves under such extreme densities. This multi-messenger astronomy, combining gravitational wave signals with electromagnetic observations, like the accompanying short gamma-ray burst from the neutron star merger GW 17817, offers an unprecedented holistic view of these violent cosmic events. All this data, often petabytes in volume, requires sophisticated computational tools for processing and analysis. Astronomers use advanced algorithms for noise reduction, searching for periodic signals, fitting theoretical models to spectral data, and processing complex images. Global collaborations are essential for sharing data and coordinating observations, especially for transient events like GRBs that require rapid, worldwide follow-up. The ultimate purpose of this extensive data collection is to build comprehensive theoretical models, test the fundamental laws of physics under extreme conditions, understand the evolution of these dangerous stars, and ultimately improve our ability to predict their behavior and assess their potential impact on the cosmos. Predicting when a dangerous star, such as a magnetar or the progenitor of a gamma-ray burst, might unleash its destructive power is one of the most challenging and complex endeavours in astrophysics. While astronomers have made significant progress in understanding the nature of these extreme objects, pinpointing the exact moment of a catastrophic event or predicting the precise trajectory of a rogue object remains incredibly difficult, largely due to the rarity of these events, the physics involved, and the vastness of space. One of the primary challenges in predicting danger stems from the inherent rarity of the most destructive events. Giant magnetar flares, capable of affecting planets across a significant portion of a galaxy, are extremely infrequent, perhaps occurring only once every few decades in the entire Milky Way. Cosmological gamma-ray bursts, while more common on a universal scale, are still relatively rare within any single galaxy over a human timescale. With so few observed events, building robust statistical models for prediction becomes challenging. Each event provides valuable but limited data points. Furthermore, the highly directional nature of gamma-ray bursts complicates prediction. GRBs emit their immense energy in narrow jets. This means that we only detect a GRB if one of these beams happens to be pointed directly at Earth. For every GRB we observe, there are likely many more that occurred with their beams pointed elsewhere in the cosmos. This makes it difficult to estimate the true rate of these explosions in our galaxy, and, more importantly, to know if a GRB that might have been devastating if aimed at us has already occurred and simply missed Earth. Predicting the precise launch direction of a GRB jet before it forms is currently impossible with our understanding of physics. Uncertainties in the underlying physical mechanisms also pose significant hurdles. While the collapsar model for long gamma-ray bursts is widely accepted, the exact conditions within the collapsing stellar core that lead to the formation and launch of relativistic jets are still subjects of active research. Similarly, the precise trigger for a magnetar giant flare, whether it is a sudden cracking of the star's crust in a starquake or a catastrophic rearrangement of its magnetic field lines, is not yet fully understood. Without a complete grasp of these intricate physics, precise short-term prediction is exceedingly difficult. For rogue objects, such as neutron stars that have been ejected from their birthplaces at high velocities, predicting their future trajectory and potential close encounters with solar systems is a formidable challenge. These objects are incredibly small and faint, making them extremely difficult to detect if they are not pulsars or part of X-ray binaries. Identifying and accurately tracking faint, isolated objects across vast cosmic distances for millions of years to predict a close pass with a solar system is currently beyond our observational capabilities. Even with future advanced telescopes, the inherent uncertainties in orbital calculations over such long timescales make precise predictions problematic. Despite these challenges, astronomers employ various methods to monitor and assess the potential danger from these stars. One approach involves the long-term monitoring of known magnetars. Astronomers continuously observe these objects with X-ray and gamma-ray telescopes, looking for subtle changes in their persistent emission, or an increase in minor bursting activity that might precede a giant flare. While no definitive pre-flare signature has been identified, ongoing observation and data analysis aim to uncover such patterns. Statistical analysis of observed GRB rates across the universe allows scientists to estimate the frequency of these events within a typical galaxy like our Milky Way. While this does not predict individual events, it provides a probabilistic assessment of the risk over geological timescales. For example, estimates suggest that a GRB aimed at Earth within a dangerous distance might occur once every hundreds of millions to billions of years, making it a very low probability but high impact event. Another method involves identifying potential progenitor stars. Astronomers search for very massive, rapidly rotating stars that are known to exist in our galaxy, and are theoretically capable of producing a long GRB when they collapse. While it is impossible to predict the exact moment any individual star will go supernova, identifying such candidates allows for monitoring and a general assessment of regions where future GRBs might originate. Similarly, studying binary systems that could merge into neutron stars, which are progenitors for short GRBs, allows for identifying potential future event sites. The advent of gravitational wave astronomy has opened a new avenue for predicting dangerous events, albeit on very short timescales. The direct detection of gravitational waves from the merger of two neutron stars provides an almost instantaneous alert to astronomers. While the event itself has already occurred, the gravitational wave signal arrives before the electromagnetic radiation, like the short gamma-ray burst, allowing astronomers to rapidly pinpoint the location and initiate follow-up observations. This allows for immediate study and characterization of these violent events, providing crucial data for improving our predictive models for future events. Furthermore, a deep understanding of the underlying physics of these extreme objects is key to improving predictive capabilities. Research into the interiors of neutron stars, the dynamics of accretion disks around black holes, and the processes that generate magnetic fields in magnetoirs constantly refines our theoretical models. These improved models help scientists better understand the conditions under which destructive power might be unleashed, even if the precise timing remains elusive. Some of the most extreme and dangerous stars in the cosmos, particularly neutron stars and magnetars, do not always remain confined within the systems or galaxies where they were born. Instead, a significant fraction of these incredibly dense objects are observed to be travelling through space at extraordinarily high velocities, often hundreds or even thousands of kilometers per second. This phenomenon is known as rogue movement, and it transforms these already dangerous objects into unpredictable cosmic wanderers, making their future trajectories difficult to predict and increasing their potential for unexpected encounters or collisions. The primary mechanism responsible for imparting these extreme velocities to neutron stars is an asymmetric supernova explosion. When a massive star, destined to become a neutron star, reaches the end of its life and explodes as a supernova, the explosion is often not perfectly symmetrical. There can be slight imbalances in the ejection of stellar material or in the emission of neutrinos, tiny, weakly interacting particles that are produced in vast quantities during core collapse. Even a tiny imbalance in these forces, when acting on the super-dense small core of the nascent neutron star, can impart a powerful kick that sends the newly formed remnant hurtling through space. These kicks can range from velocities of a few tens of kilometers per second to well over 1,000 kilometers per second, far exceeding the typical orbital speeds of stars within a galaxy. For instance, some neutron stars have been observed with velocities exceeding 1,000 kilometers per second, enough to escape the gravitational pull of our entire Milky Way galaxy. Another mechanism for generating rogue movement, though typically resulting in somewhat lower velocities than supernova kicks, is gravitational slingshot or ejection within dense stellar environments. This often occurs in regions like globular clusters, which are tightly packed collections of hundreds of thousands of stars, or near the supermassive black hole at the center of a galaxy. In such crowded environments, close gravitational encounters between three or more massive objects can lead to a powerful transfer of energy. One object might gain a significant amount of kinetic energy at the expense of others, leading to its ejection from the cluster or galactic core at high speed, while the other objects settle into tighter orbits. If a neutron star is involved in such a three-body interaction, it can be flung out as a rogue. Similarly, if a binary star system undergoes a supernova, the explosion can sometimes unbind the remaining two objects, sending them flying in opposite directions as unbound rogue stars. The characteristics of rogue movement are distinct. Unlike the vast majority of stars in a galaxy, which follow relatively predictable orbits around the galactic center, within the galactic disk, rogue neutron stars typically possess trajectories that are highly inclined to the galactic plane, or even directed out of the galaxy entirely. Their high velocities mean they can quickly escape the gravitational influence of their original stellar cluster, or even their home galaxy. Once unbound, they travel through intergalactic space, only weakly influenced by the gravitational fields of distant galaxies. Within a galaxy, their paths do not conform to the general rotation pattern of stars in the disk, making them stand out due to their distinct velocities and directions of motion. Predicting the precise trajectories of these rogue stars over long timescales, millions or billions of years into the future, is incredibly challenging. Firstly, isolated neutron stars are inherently difficult to detect. Being only about 12 miles in diameter and typically emitting very little visible light, they are nearly invisible against the cosmic backdrop, unless they are actively accreting matter from a companion, acting as a pulsar, or flaring as a magnetar. Many rogue neutron stars are thought to be completely dark and silent, making them almost impossible to track until they pass relatively close to our detection range. Even when they are detectable, their faintness and distance make precise astrometric measurements, necessary for determining their motion, very difficult. Secondly, even small errors in initial measurements of a rogue star's position, velocity and direction can amplify significantly over the vast cosmic distances and timescales involved. Predicting a precise close encounter with another star or a planetary system millions of years in the future requires extreme accuracy in the initial data. The subtle gravitational influences from the distribution of dark matter and other stars throughout the galaxy can also slightly perturb their paths, adding further complexity to long-term predictions. Knowing the origin point of a rogue star, which is often obscured by galactic magnetic fields and the passage of time, is also crucial for modelling its full trajectory, but this information is frequently unavailable. The implications of rogue movement for potential cosmic encounters are significant, despite the rarity of such events. While the universe is vast and mostly empty, the high velocities of rogue stars mean they sweep through a larger volume of space over time, slightly increasing the probability of an encounter compared to a stationary object. An unexpected close flyby of a rogue neutron star, even without a direct collision, could have profound gravitational consequences for a planetary system. As discussed in previous topics, its immense gravitational pull could perturb planetary orbits, potentially ejecting planets from their home star, sending them on collision courses, or triggering a shower of comets and asteroids from outer solar system reservoirs like the Oort cloud. Such encounters would be unexpected due to the rogue star's non-standard trajectory. Although exceedingly rare, the possibility of a direct collision between a rogue neutron star and another star or a planet exists in theoretical models. If such an event were to occur, the sheer energy released would be immense, far surpassing any other known cosmic collision. Even passing through a dense gas cloud in a star-forming region, a more likely scenario, can cause significant disruption, heating and dispersing the gas, or potentially triggering localized star formation. The extreme conditions created by the rogue star ploughing through dense interstellar medium can also lead to the emission of X-rays or gamma rays, further highlighting its dangerous nature. Observational evidence for rogue neutron stars has been accumulating. Astronomers identify them by looking for objects with unusually high proper motion, which is their apparent movement across the sky over time, indicating a high space velocity. For pulsars, their radio signals can be analysed for Doppler shifts, which reveal their speed relative to Earth. The absence of a visible supernova remnant or a companion star also supports the rogue hypothesis. Some rogue neutron stars create distinct bow shocks as they plough through the interstellar medium, compressing the gas ahead of them and illuminating it, providing visual evidence of their high-speed passage. These observations confirm that rogue movement is a common outcome for these extreme stellar remnants, making them true cosmic projectiles in the galactic landscape. While the vastness of space often implies isolation, celestial bodies, including dangerous stars like neutron stars and magnetars, are not static. They can participate in various forms of cosmic collisions, ranging from exceedingly rare direct impacts between stars to more common, though still immense, interactions between galaxies. The involvement of a dangerous star in such a collision can dramatically amplify the resulting chaos, leading to widespread gravitational disruption, intense radiation bursts, and altered cosmic environments. The most extreme and rarest form of collision involving a dangerous star is a direct star-on-star impact. While stars are numerous within a galaxy, the distances between them are immense, typically light years apart. Even in crowded regions like globular clusters or galactic cores, direct stellar collisions are exceedingly improbable. However, if a rogue neutron star travelling at thousands of kilometers per second were to somehow find itself on a collision course with a normal star, the outcome would be cataclysmic. A direct hit would unleash an immense amount of kinetic energy, likely resulting in the complete destruction and vaporization of the normal star. The neutron star, being incredibly dense and compact, would likely survive the encounter, perhaps gaining mass, accelerating further, or being heated to emit a burst of radiation. More likely than a head-on collision is a grazing encounter, where the neutron star might strip away layers of the companion star through powerful tidal forces, leading to a burst of X-rays as the accreting material superheats. Even rarer, but theoretically possible, is a direct collision between a rogue neutron star and a planet. The scale difference between a star and a planet, coupled with the vast emptiness of space, makes this an exceptionally remote possibility. However, if such an event were to occur, the planet would be utterly destroyed. The neutron star's overwhelming gravity would tear the planet apart through extreme tidal forces long before a physical impact, turning it into a stream of superheated plasma that would then be absorbed by the neutron star. The energy released from the disruption and accretion of the planetary material would be immense, likely manifesting as a powerful burst of X-rays and potentially gamma rays. A more plausible type of collision for a dangerous star is an encounter with a gas and dust cloud such as a nebula or a star-forming region. As a rogue neutron star, especially one travelling at high velocity, ploughs through a dense molecular cloud, the interaction would be dynamic. The star would create a strong bow shock as it compresses the interstellar medium ahead of it, heating the gas to X-ray emitting temperatures. The passage could trigger localized star formation due to the compression of gas, or conversely, it could disrupt and disperse fragile regions of the cloud, hindering ongoing star formation. If the rogue star is a magnetar, its incredibly powerful magnetic field could also interact with and locally disturb the magnetic fields within the cloud, potentially affecting the cloud's stability and dynamics. These interactions, while not collisions in the sense of two solid bodies impacting, represent significant energy exchanges that can reshape the interstellar environment. The larger context for collisions involving dangerous stars often arises during galactic mergers. Galaxies are not static entities. They move through the universe and can interact and collide with one another. Our own Milky Way galaxy is currently on a collision course with the Andromeda Galaxy, an event predicted to occur in about 4.5 billion years. While galactic mergers are cosmic spectacles, it is crucial to understand that direct star-on-star collisions are still exceedingly rare even during such events. This is because the distances between stars within galaxies are so vast that galaxies are mostly empty space. When two galaxies merge, their constituent stars mostly pass through each other like ghosts, their paths slightly perturbed by the gravitational fields of the other galaxy. However, a galactic merger significantly increases the probability of gravitational encounters, which can still lead to chaotic outcomes involving dangerous stars. During a merger, the gravitational fields of the two galaxies become highly disturbed and complex. This can lead to increased rates of close encounters between individual stars, triggering gravitational slingshot events that could eject neutron stars or other objects from their systems at high velocities, further contributing to the population of rogue stars. Planetary systems could be gravitationally perturbed, leading to altered orbits or even ejection into intergalactic space. The increased gas density and compression that often occur during mergers can also lead to bursts of star formation, which in turn means more massive stars and thus more supernovae, and potentially more neutron stars and magnetars being born in a relatively short period. In the cores of merging galaxies, where supermassive black holes reside, the interactions can become even more extreme. A rogue neutron star could be captured by the supermassive black hole's gravity, forming a tight orbit or even spiraling into the black hole. The final moments before being consumed would release immense amounts of energy, potentially detectable as X-ray flares or gravitational waves. Similarly, if a dwarf galaxy, which might contain its own dangerous stars, were to merge with a larger galaxy, its stars would be incorporated into the larger system, increasing the overall population of stars and potentially the density of dangerous objects. The chaos resulting from these collisions, particularly galactic mergers, is widespread. It leads to widespread gravitational disruption, fundamentally reshaping the overall structure of the merging galaxies. Star-forming regions can be compressed, leading to bursts of new star birth, but also to the dispersal of gas clouds and the destruction of existing stellar nurseries. High-energy radiation can be produced by accretion onto black holes or by increased supernova rates. The overall effect is a violent rearrangement of stellar populations, gas, and dark matter, leading to a new, larger, and often more elliptical galaxy. The dangerous star in these scenarios is both a product and a participant in the large-scale cosmic violence, contributing its own localized destructive potential to the grand cosmic rearrangement. Despite their destructive capabilities, these collisions are fundamental processes that drive galactic evolution, recycling matter and reshaping the universe over billions of years. The universe, on its largest scales, is not a uniform, haphazard distribution of galaxies. Instead, it forms an intricate and vast network known as the cosmic web. This structure, comprised of immense filaments, dense clusters, and vast, nearly empty voids, represents the fundamental scaffolding of the cosmos. Understanding the cosmic web is essential to grasping the universe's large-scale organization. However, the question of how a single destructive star, even one as powerful as a magnetaire or a supernova, could impact this delicate balance requires appreciating the vast difference in scale between individual stellar events and the colossal architecture of the universe. The cosmic web is a direct consequence of the gravitational collapse of primordial density fluctuations in the early universe. After the Big Bang, matter was not perfectly smooth. There were tiny variations in density. Over billions of years, gravity slowly amplified these initial ripples, pulling matter from less dense regions into denser ones. This process led to the formation of the web-like structure we observe today, where galaxies are not randomly scattered, but are concentrated along lines and knots, while vast empty spaces yawn between them. The primary components of the cosmic web are, firstly, filaments, which are long thread-like structures composed of galaxies, gas, and dark matter. These filaments can stretch for hundreds of millions of light-years and serve as cosmic highways, channeling matter towards larger gravitational wells. Secondly, galaxy clusters, which are the densest knots in the cosmic web, located at the intersections of filaments. These are massive structures containing hundreds or even thousands of galaxies, along with vast amounts of hot intergalactic gas and a dominant component of dark matter. Clusters are the largest gravitationally bound structures in the universe. Thirdly, voids, which are immense, nearly spherical regions that are almost entirely devoid of galaxies and contain very little gas or dark matter. These voids can span hundreds of millions of light-years, representing the underdense regions from which matter was pulled away by gravity. And finally, the galaxies themselves, which are the visible luminous parts of the cosmic web, residing predominantly along the filaments and within the clusters. They are held together by the gravity of their own stars, gas, dust, and dark matter halos. The cosmic web is fundamentally shaped and held together by gravity, and its evolution is dominated by the mysterious dark matter, which provides the gravitational scaffold and dark energy which drives the accelerated expansion of the universe, causing the web to stretch and grow. The delicate balance of the cosmic web refers to the interplay between the inward pull of gravity, which tries to collapse structures, and the outward push of dark energy, which tries to pull them apart, as well as the ongoing flow of gas and galaxies along the filaments. Considering the scale, a single dangerous star, even one as energetic as a supernova or a magnetar, is infinitesimally small compared to the vastness of the cosmic web. A typical star is only millions of miles in diameter, while a neutron star is merely 12 miles across. A galaxy itself is tens of thousands to hundreds of thousands of light-years across, and a filament of the cosmic web can span hundreds of millions of light-years. The difference in scale is analogous to trying to impact a global road network by stomping on a single ant. Therefore, a single destructive star cannot directly break or unbalance the large-scale structure of the cosmic web. Its gravitational influence is far too localized to affect the dynamics of entire filaments or clusters. The cosmic web structure is dictated by the gravity of billions of galaxies and trillions of tons of dark matter, operating on cosmological scales, not by individual stellar events. The overall distribution of matter, the expansion of the universe, and the dark matter gravitational potential wells are orders of magnitude more dominant in shaping the web. However, a single dangerous star can have localized indirect influences on the components within the cosmic web. For instance, firstly, local chemical enrichment, supernovae, the birth events of neutron stars and magnetars, are vital for dispersing heavy elements throughout galaxies. As galaxies reside within the filaments and clusters of the cosmic web, the cumulative effect of countless supernovae over cosmic time enriches the gas within these structures with elements heavier than hydrogen and helium. While one supernova is a single point, its contribution, along with others, means that the gas flowing along filaments and into clusters is gradually becoming more chemically diverse, allowing for subsequent generations of stars and planets to form with more complex compositions. This is a very localized ripple for a single event, but contributes to the larger chemical evolution of matter within the web. Secondly, gas heating and ionization. A powerful supernova or a gamma-ray burst can heat and ionize the diffuse gas within a galactic halo, or even in the intergalactic medium directly along a filament. This intense heating and ionization could locally affect the ability of gas to cool and fall into galaxies, thereby slightly influencing the ongoing process of galaxy formation and growth within that specific region of the web. However, the energy input from a single event is dwarfed by the overall thermal and ionization state of the intergalactic medium, which is heated by shock waves from large-scale structure formation and radiation from active galactic nuclei. Thirdly, propagation of star formation. As discussed, supernova shock waves can trigger localized star formation within galaxies that are part of the cosmic web's filaments. This contributes to the ongoing stellar activity within these galaxies, which are themselves part of the larger web structure. A rogue neutron star traveling at high velocity might traverse parts of a filament, potentially interacting with gas clouds or stellar systems along its path. But again, these are localized interactions within the components of the web, not impacts on the web's overarching framework.